Imagine a high-security vault where every item has a specific shelf, tracking tag, and automated backup system. That is exactly what Azure Storage provides for your applications. It is not just a hard drive in the cloud. It is a highly distributed service that handles petabytes of data with built-in redundancy and global accessibility. In this lesson, we will explore how to architect, secure, and manage storage accounts to ensure your data is safe, fast, and cost-effective. We will start by reviewing the core storage services and how they differ. Next, we will dive into account architecture and redundancy strategies like standard LRS versus GZRS. Then, we will walk through a step-by-step process for creating a storage account using the Azure Storage Account Create CLI command. After that, we will cover security configurations, access tiers, and lifecycle management policies. Finally, we will look at monitoring with application insights and troubleshooting common egress bottlenecks. Skipping these steps often leads to unexpected billing spikes or failed disaster recovery drills during certification exams. Azure Storage provides 4 primary services, each optimized for a specific data type. Blob storage handles unstructured data like images and logs through the Azure Storage blob upload command. Azure Files offers managed file shares accessible via SMB protocol for legacy application migration. Queues store large numbers of messages for asynchronous processing between microservices. Tables provide a NoSQL key attribute store for structured non-relational data at scale. Choosing the wrong service typically causes severe latency spikes and unnecessary transaction fees during peak traffic windows. A shared access signature is a URI that grants restricted access to storage resources without exposing your account keys. You define exactly which resources are accessible, what permissions apply, and when the link expires using the Azure Storage Container Generate SaaS command. This follows the principle of least privilege, ensuring that only authorized users or services can interact with specific blobs or files for a limited window. Forgetting to set an expiration timestamp often leaves your endpoints permanently vulnerable to unauthorized data exfiltration attempts. Let us walk through creating a storage account step by step. First, we define the performance tier and redundancy strategy to match your data criticality. You must select either standard or premium page blobs depending on whether you are storing standard workloads or high-performance virtual machine disks. Picking an incompatible tier immediately breaks application connectivity and triggers costly support tickets. We will configure these parameters before provisioning any actual data containers. We start by creating a resource group to organize our assets. Then we run the Azure Storage Account Create command, specifying standard LRS for cost-effective local redundancy and storage v2 as the modern general-purpose kind. For example, running this in the Eastis region establishes 3 copies within a single data center. This configuration establishes the foundation for all subsequent data operations. Misaligning your tier with your workload type quickly inflates monthly egress costs and degrades read throughput significantly. Next, we configure network access rules to restrict traffic. We disable public access by default and allow connections only from specific virtual networks using private endpoints. You will update the network ACL's block to explicitly deny all inbound internet traffic while whitelisting your internal subnet CIDR ranges. This approach prevents accidental exposure of sensitive logs or customer records. Skipping this step frequently results in compliance audit failures and unexpected data leakage across public IP addresses. Here we update the account to disable public network access entirely. We set the default action to deny and then add a specific subnet rule to allow traffic from our internal virtual network using the Azure Storage Account Update CLI. This ensures data only flows over the Azure backbone without traversing the public internet. Forgetting to append your on-premises CIDR range will immediately lock out all legitimate database connections and halt production deployments completely. Finally, we validate the configuration and deploy the resource. We verify the SKU, kind, and network settings to ensure everything matches our architectural requirements before production use. You will run a quick AZ storage account, show query to confirm that public network access is disabled, and the redundancy mode aligns with your compliance checklist. Failing this validation step often leads to misconfigured firewalls that accidentally expose internal endpoints to external threat actors during peak hours. We run the show command to query the current SKU name, account kind, and public access status. The output table confirms that standard LRS is active and network access is disabled as intended. You will cross-reference these fields against your security baseline documentation before provisioning any blob containers. This verification step prevents misconfigurations in production. Overlooking validation frequently causes cascading authentication failures when applications attempt to connect through restricted firewall rules. Access tiers optimize costs based on how frequently you retrieve data. The hot tier suits frequent access with higher storage fees but lower transaction costs. The cool tier reduces storage costs for data kept at least 30 days, while the archive tier offers the cheapest storage for rarely accessed backups, albeit with retrieval latency. You should configure lifecycle management policies to automatically migrate blobs from hot to cool after 90 days. Ignoring these tiers typically inflates monthly bills by over 40% due to unnecessary premium storage charges. Data flows through Azure Storage with built-in replication. A user request hits the primary region for immediate read or write operations. The system then asynchronously replicates changes to a secondary paired region using synchronous write acknowledgements. This ensures that if the primary site fails, data remains available and durable across geographic boundaries. Failing to configure geo-redundant storage leaves your disaster recovery plan completely unprotected against regional infrastructure outages lasting several hours. Scalability targets define the throughput limits of a storage account. A standard general-purpose V2 account has specific ingress and egress limits, but they are not infinite. You will hit maximum request rates around 1,000 transactions per second before encountering any bottlenecks. If your application expects millions of concurrent users, you must distribute data across multiple storage accounts to avoid throttling and 53 server busy errors. Ignoring these caps immediately degrades user experience and triggers expensive support escalations during peak traffic windows. Security should never be an afterthought. Always default to the principle of least privilege and use managed identities to eliminate key management overhead entirely. You will assign the storage blob data reader role directly to your virtual machine rather than embedding connection strings in application code. This approach prevents accidental credential leakage during repository commits or debug logs. Neglecting identity management consistently exposes your entire storage infrastructure to unauthorized access and compliance violations. Which redundancy option keeps 3 copies locally and replicates 3 more to a secondary, paired region hundreds of miles away, providing the gold standard for disaster recovery? You will need to select geo-redundant storage from your exam scenario options. This configuration guarantees 99.9% availability while automatically failing over during regional outages. Choosing local redundancy instead leaves your critical databases completely exposed to permanent data loss if a single data center experiences a catastrophic hardware failure. We covered the core storage services and how to match them to data types. You learned how to create accounts with specific redundancy and networking configurations using the Azure CLI. We discussed access tiers, lifecycle management policies for cost optimization, and strict scalability targets. Finally, we reviewed monitoring strategies with log analytics to maintain performance and security. Mastering these fundamentals directly prevents billing surprises and ensures your applications meet enterprise compliance standards during certification exams. For the AZ-305 exam, focus on selecting the right redundancy strategy based on our TO and our PO requirements. Know how to configure private endpoints for secure access using subnet delegation. Understand lifecycle management policies for cost optimization by setting automatic tier transitions after 30 days. Always choose managed identities over shared keys in scenario-based questions. Failing to prioritize identity-based authentication over legacy connection strings will consistently mark your answers as incorrect on the performance assessment. Imagine you're shipping valuable packages across the country without insurance. One accident and your goods are gone forever. In cloud computing, storage accounts act as your insured logistics network, ensuring data survives hardware failures, regional disasters, and accidental deletions. Today, we will master how to select the right account type for performance and choose replication strategies that keep your applications resilient under pressure. You must configure these correctly or face costly downtime during certification scenarios and production outages. Here is our roadmap for this lesson. First, we will explore storage account tiers and use cases to distinguish between standard and premium options. Second, we will break down replication strategies explained, covering LREs through RGREs. Third, we will focus on designing resilient solutions by weighing cost against recovery objectives. Finally, we will walk through implementing with infrastructure as code using real Azure CLI commands. Mastering this sequence ensures you pass the exam and avoid misconfigured resources in production environments. Azure offers two main families of storage accounts: standard and premium. Standard accounts use hard disk drives for cost-effective storage and are the default choice for most workloads. They support blobs, files, queues, and tables. Premium accounts rely on solid-state drives to deliver high throughput and sub-millisecond latency. You should only choose premium when your application demands intense I/O operations or consistent low-latency responses. Selecting standard incorrectly will cause severe performance bottlenecks for latency-sensitive databases. Let's define a critical term you will see on the exam: read access geo-redundant storage, or RGREs. This strategy builds upon GREs by allowing you to read data from the secondary region even when the primary region is healthy. This is essential for active-active scenarios where you might want to offload read traffic to the secondary site to reduce latency or load on the primary. Failing to configure this properly will force all client requests through a single endpoint, causing unacceptable network congestion during peak hours. When comparing replication strategies, you must balance protection against cost. LREs keeps data within one data center and is the cheapest option, but offers no disaster recovery. ZREs protects against data center failures by spreading copies across availability zones. GREs replicates to a paired region for full regional disaster protection. RGREs adds read access to that secondary region for advanced failover needs. Choosing the wrong tier will either waste budget on unnecessary redundancy or leave your workload vulnerable to sudden regional outages. Visualizing how data flows during replication helps clarify the differences. When you write to a storage account, the data is first committed to the primary region. From there, it is asynchronously replicated to a secondary paired region. This secondary copy ensures that if the entire primary region goes offline due to a disaster, your data remains intact and recoverable in the secondary location. Misunderstanding this asynchronous lag can cause you to lose uncommitted transactions during sudden hardware failures. Now let's move to implementation. We will use infrastructure as code to provision a resilient storage solution. The first step is creating a resource group named Prod Storage RG in the East US region using the as group create command. This establishes the logical container and defines the initial location for all dependent resources. Skipping this foundational step will cause deployment failures when subsequent commands reference missing parent identifiers. We start by creating a resource group using the Azure CLI. This command establishes the logical container for our storage account and sets the initial location to East US. The resource group acts as the parent object that holds all related resources for this solution. Executing as group create correctly prevents orphaned resources from accumulating in your subscription and complicating monthly cost audits. With the resource group in place, we proceed to the second step, configuring the storage account itself. Here we select the SKU for standard GRS and specify the kind as storage v2 to support all modern blob features. This command defines the replication strategy and performance tier. Misconfiguring these parameters will lock you into legacy IPI versions that lack lifecycle management capabilities. Next, we deploy the storage account with a GREs replication strategy. The SKU is set to standard GRS to ensure data is copied to a paired region for disaster recovery. We also specify storage v2 as the kind, which enables blob storage features and lifecycle management capabilities. Running as storage account create without these exact flags will default to local redundancy, exposing your architecture to single-region catastrophic failure. Finally, we apply best practices to harden the storage configuration. This step involves enabling soft delete for blobs to prevent accidental data loss and configuring lifecycle policies to manage costs. These settings ensure your storage is not only resilient, but also optimized for operational efficiency. Neglecting these configurations will force you to manually restore files or pay premium pricing for unmanaged hot-tier data. We finalize the setup by enabling soft delete for blobs and configuring a lifecycle policy. This command updates the blob service properties to retain deleted blobs for 7 days, providing a safety net against accidental deletions. It also sets up automated tiering to move older data to cooler storage tiers. Overlooking this update will permanently erase critical files when developers accidentally overwrite production datasets. Resilience is a design choice, not an afterthought. Choosing the right replication strategy and storage tier upfront prevents costly downtime and data loss later. Always align your storage architecture with your recovery objectives from the very beginning. Ignoring these architectural decisions will result in failed certification assessments and unpredictable SLI breaches during live traffic spikes. Let's check your understanding. You need to design a storage solution for a critical application that requires read access from the secondary region even when the primary is healthy. Which replication strategy should you choose? Consider the options we discussed regarding read access capabilities. Selecting standard GREs instead will block your failover tests and cause immediate service interruptions when developers query the inactive endpoint. Let's recap what we have learned. We explored standard versus premium storage accounts, noting that standard is sufficient for most workloads while premium suits high-performance needs. We compared replication strategies from LREs to RGREs, emphasizing the importance of secondary read access. Finally, we implemented a resilient storage solution using infrastructure as code with CLI commands. Mastering these concepts ensures you configure compliant environments and avoid exam scenario traps. For the AZ-305 exam, focus on matching scenarios to the correct replication strategy. Pay close attention to keywords like active-active, which point to RGREs, or data center failure, which suggests ZREs. Remember that GREs replicates to a paired region only, and never hardcode storage keys in your applications. Use managed identities instead. Review the CLI commands for creating storage accounts, as they often appear in practical scenarios. Misreading these prompts will lead you to select incorrect SKU options during timed assessments. Imagine a library where you pay rent for every single inch of shelf space. If you stash bestsellers in the deep stacks while keeping reference books on the front desk, your monthly bill instantly explodes. Cloud storage operates exactly like that rental model. Storing everything on premium performance drains your budget fast. To build cost-effective architectures, you must match each blob tier to actual access frequency. Today, we will master hot, cool, and archive tiers alongside lifecycle automation that prevents costly retrieval traps during production deployments. We will start by breaking down the 3 core blob tiers and their precise trade-offs between cost, latency, and access frequency. Next, we will examine the exact JSON structure of Azure Storage lifecycle policies to understand how automation executes under the hood. Then we will walk through a step-by-step implementation chain using the Azure Storage blob CLI to configure transitions, retention windows, and prefix filters in practice. Finally, we will cover critical best practices, highlight the retrieval trap pitfall, and share targeted exam tips for the AZ-305 certification. Let's examine the 3 primary tiers directly. The hot tier delivers sub-millisecond latency with higher storage costs per gigabyte, making it ideal for active website images where performance cannot lag. The cool tier drops storage prices significantly, but introduces slightly higher retrieval fees and strict 24-hour minimum storage requirements. It targets data stored for at least 30 days that you rarely access. Finally, Archive provides the absolute lowest storage cost, but carries high retrieval fees and significant latency, often requiring 48 hours to rehydrate data before your applications can read it. Data flows through these tiers strictly based on modification age and access patterns. When a blob is initially created, it automatically starts in hot storage. As it ages past 30 days without modification, the lifecycle policy quietly shifts it to cool tier. Once it passes 90 days, it moves to archive for long-term compliance. After your specified retention period ends, the policy permanently deletes the blob entirely. This automated flow prevents runaway costs and ensures you never pay premium performance fees on stale data that has aged out of active use. This entire process is governed by Azure Storage Lifecycle Management. This service allows you to define precise rules that automatically move blobs between tiers or delete them based on age, access patterns, or custom metadata tags. Instead of manually moving files through the portal, you write a JSON policy once and let the system enforce the transitions. This automation is critical for maintaining cost efficiency at scale across petabytes of data, preventing manual errors that could accidentally delete active workloads or leave expensive hot storage running indefinitely. Now let's implement a lifecycle policy step by step using the Azure Portal or CLI. First, you define the tier transitions. This is where you specify exactly which actions trigger when a blob reaches a certain age threshold. You will configure moves to cool and archive based strictly on modification dates. This establishes the primary flow of your data through the storage tiers. ensuring that active logs automatically downshift while preventing accidental deletions before compliance windows close. Here is how you define those transitions in JSON format. The base blob object contains the core actions for standard block blobs. We set tier to cool to trigger after exactly 30 days of modification and tier to archive after 90 days. This code block establishes the automatic movement logic that drives your data flow from hot storage down to archive, preventing unexpected egress fees if you forget to route older logs through the correct lifecycle rules. Let's compare the tiers side by side to solidify the exact trade-offs. Hot offers sub-millisecond latency, but higher storage costs, making it ideal for active web workloads. Cool reduces storage costs significantly, but introduces slightly higher retrieval fees and 24-hour minimum durations. Archive provides the cheapest storage of all but incurs high retrieval costs and can take hours to access data. Always weigh these factors against your application's requirements before configuring moves, or you will trigger expensive rehydration penalties during peak traffic. Next, we configure retention and deletion rules directly in the policy editor. Once data sits in cool or archive, you must decide exactly when to remove it entirely to save space. You define a delete action with a specific day threshold, typically matching regulatory windows. This ensures that compliance records or logs are purged automatically after their required retention period expires, preventing storage bloat and avoiding accidental deletion of active audit trails before legal holds finish. In this policy snippet, we add the deletion logic directly to the base blob section. We specify delete with a threshold of exactly 365 days. This rule ensures that after 1 full year of storage, the blob is permanently removed from your container. This cleanup step is essential for long-term cost control and compliance management, preventing runaway storage bills while guaranteeing you never accidentally purge data before mandatory audit windows close. Finally, you apply filters to scope the policy precisely across your storage account. Filters determine exactly which blobs the rule applies to, preventing accidental changes to unrelated data. You can use blob types to target block blobs only or prefix match to restrict the rule to specific folders like logs or backups. This precision ensures your automation affects exactly the right datasets, avoiding catastrophic misrouting that could delete critical application binaries or leave unmanaged files accumulating in hot storage. Here we see the filters in action within the JSON editor. We set blob types to target only block blobs, explicitly excluding page or append blobs from this rule. Then, we add a prefix match for the logs folder, ensuring this lifecycle rule only applies to data inside that specific path. This scoping prevents the policy from affecting other containers or file types in your storage account, avoiding accidental tier shifts that could break dependent application pipelines. Remember this principle strictly. Automation is absolutely key for production environments. Never manually move blobs between tiers using the portal or CLI in active workloads. Use lifecycle policies to enforce data retention and tiering automatically across all containers. Manual moves are highly error-prone and do not scale, whereas automated policies ensure consistent cost optimization and prevent accidental deletion of critical files before compliance windows expire. Let's check your understanding with a practical scenario. You have a compliance dataset that must be retained for exactly 5 years, but is accessed only once a year. Which tier and action combination best fits this requirement? Think carefully about the extremely low access frequency and the strict long-term retention need. Choosing hot storage will trigger massive unnecessary costs, while archive requires rehydration fees that waste budget on rarely used records. To recap, we covered the 3 blob tiers and their precise trade-offs between cost and access frequency. We explored lifecycle policy structure and implemented transitions, retention rules, and prefix filters step by step. Remember to use prefixes for strict scoping, monitor actual access patterns to avoid retrieval traps, and always account for minimum storage durations when designing your data strategy, or you will face unexpected egress charges during peak audit periods. For the exam, focus on recognizing when to use each tier based strictly on scenario descriptions. You will likely encounter questions about optimizing costs for specific workloads like application logs or weekly backups. Pay close attention to minimum storage durations and retrieval times listed in the answer options. Also, remember that lifecycle policies apply directly to blobs within a container, and you must configure filters correctly to target the right data while avoiding misconfigured rules that delete active snapshots. Imagine you are running a busy restaurant. You need ingredients delivered quickly to the kitchen. If you use a slow courier, your chefs wait. Azure Files acts as that reliable courier delivering shared files to your apps, while NetApp Files serves as the high-performance partner for demanding workloads. In this lesson, we will explore how to choose and design the right file storage solution for your cloud architecture. We begin by examining Azure Files and its core SMB and NFS protocols. Next, we dive into NetApp Files for extreme performance requirements. We will compare these services side by side to clarify exactly when to use each one during the exam. Then, we walk through a design pattern for selecting storage based on specific workload metrics. Finally, we cover security best practices like private endpoints and critical exam tips to avoid common pitfalls. Azure Files provides fully managed file shares accessible via SMB and NFS protocols. This means legacy applications require zero code changes to integrate with cloud storage. You can mount these shares on Windows Server or Ubuntu VMs as standard network drives. The platform automatically handles disk provisioning and patching for you, which prevents costly downtime during infrastructure updates while letting developers focus entirely on application logic. To master Azure Files, you must understand the underlying protocols. SMB version 3 serves as the standard for Windows environments, handling file sharing and printer spooling securely over TCP port 445. NFS version 3 and 4 operate within Linux workspaces, optimizing RED operations through UDP or TCP. Knowing these differences prevents connection timeouts and ensures your virtual machines mount shares correctly during deployment. Let us examine mounting a share on an Ubuntu virtual machine using the Azure CLI. You run sudo mount tsif//storage account file core Windows net/sharename/mnt/share overs equals 3 0 username equals my account password equals Yorkie dire mode equals 0777 file mode equals 0777. This command explicitly binds the network drive to your local directory structure. Failing to set strict directory permissions often triggers access denied errors when applications attempt to write configuration files or logs. Here is a direct comparison between Azure Files and NetApp Files. Azure Files handles standard lift-and-shift migrations with premium tier options delivering up to 60,000 IOPS per share. NetApp Files targets extreme latency requirements under 5 milliseconds for databases like SIPHANA. Management also shifts dramatically, as NetApp requires manual capacity pool sizing rather than automatic PAS scaling. Now let us design a production solution using a cumulative approach across 3 architectural steps. First, you analyze baseline workload metrics to calculate exact IOPS and megabyte throughput requirements. This initial assessment prevents performance bottlenecks before deployment. You must document expected concurrent user sessions and average file sizes to establish a reliable baseline for your storage configuration. To analyze workload requirements, you query log analytics using a targeted KQL statement. The query filters storage metrics where latency exceeds 200 milliseconds over the last 24 hours. This threshold identifies slow disk operations before they cascade into application timeouts. Adjusting the aggregation interval reveals daily usage spikes that trigger capacity scaling decisions. Next, you select the exact service tier based on those calculated metrics. Standard lift-and-shift migrations perform adequately on Azure Files Premium with 40,000 provisioned IOPS. Extreme database workloads require NetApp Files with dedicated capacity pools sized at 10 terabytes minimum. Skipping this sizing step often results in throttled write operations that crash transactional applications. Here is a bicep template snippet for provisioning a NetApp capacity pool. You define the premium tier with 250 megabytes per second throughput and 20,000 IOPS. The configuration explicitly binds the pool to your East US region and designated resource group. Forgetting to allocate sufficient throughput guarantees severe application throttling during peak database transactions. Finally, you implement strict network security and identity controls across the architecture. You deploy private endpoints to route all SMB traffic exclusively through the Azure Backbone subnet. Enabling secure transfer forces TLS version 1.2 encryption on every connection. Relying on shared access signatures instead of Entra ID roles exposes your storage account to credential theft during automated deployments. This bicep configuration demonstrates creating a private endpoint for your storage account. The resource explicitly links the endpoint interface directly to the Microsoft Storage File Service Subnet Identifier. You must assign a dedicated private IP address within your virtual network range. Misconfiguring this linkage inadvertently opens public endpoints that expose sensitive data to unauthorized external networks. Remember this core architectural principle. Align storage performance metrics directly with workload intensity rather than raw capacity limits. Over-provisioning premium tiers unnecessarily inflates monthly billing by exceeding actual transaction volumes. Under-provisioning causes severe latency spikes that crash production databases. Always validate concurrent IOPS thresholds before committing to a final service tier. Let us check your understanding with a practical scenario. You manage a legacy application requiring SMB protocol access and moderate IOPS around 5,000. Which service would you recommend for this environment? Consider the trade-offs between automatic PAS management and complex capacity pool configurations. Choosing incorrectly will either waste budget or cause severe performance degradation. This diagram illustrates the exact data flow for a secured Azure Files deployment. The client virtual machine connects through a dedicated subnet directly to a private endpoint. Traffic routes exclusively across the Microsoft Azure Backbone network, completely bypassing public internet gateways. Bypassing this secure path exposes sensitive configuration files to external interception and unauthorized access attempts. We have covered the essential differences between Azure Files and NetApp Files. Azure Files delivers managed SMB shares for standard lift-and-shift migrations, while NetApp provides sub-millisecond latency for enterprise databases. You designed a secure architecture by analyzing metrics, selecting appropriate tiers, and enforcing private endpoints. Always prioritize Entra ID role assignments over static storage keys to prevent credential leaks. Focus your exam preparation on distinguishing between PAS management models and capacity planning requirements. You will encounter questions testing whether you recognize when to use Azure Files versus NetApp capacity pools. Practice calculating exact IOPS thresholds for specific workloads like SIPHANA or SQL Server. Mastering these distinctions prevents costly architectural mistakes during production deployments. Imagine moving into a fully furnished apartment where the plumbing works immediately and you never worry about separate utility bills. That is exactly how Azure Managed Disks function for your virtual machines. The platform automatically provisions storage accounts, handles scaling, and manages maintenance behind the scenes. This eliminates manual infrastructure overhead and prevents costly misconfigurations. You can focus entirely on deploying applications while relying on built-in high availability and automated backup integration for production workloads. We will start with core managed disk fundamentals, then compare premium SSD v2 against standard HDD tiers to match specific performance requirements. You will learn the exact as-disk create CLI syntax for provisioning storage. We will also examine security configurations and automated backup strategies before addressing IOPS throttling and unformatted block devices that frequently cause exam failures. Mastering these components ensures your architecture meets compliance standards while avoiding unexpected downtime during peak traffic windows. A managed disk is a dedicated block-level storage volume that Azure automatically provisions and maintains for your virtual machines. Instead of manually creating storage accounts to host VHD files, the platform abstracts away the underlying infrastructure completely. Azure distributes data across multiple scale units to eliminate single points of failure. This architecture prevents costly misconfigurations and ensures consistent latency, while allowing you to attach disks directly using standard as VM disk attach commands without managing separate resource groups. Managed disks deliver 4 critical advantages that streamline cloud storage architecture. Simplified administration removes the overhead of tracking separate storage accounts or VHD blobs. Automatic distribution across storage scale units guarantees higher availability and prevents data corruption during node failures. Dynamic scaling lets you upgrade to larger disk sizes without rebooting most virtual machine families. Enhanced security integrates seamlessly with Azure Disk Encryption and customer-managed keys, protecting sensitive workloads from unauthorized access while meeting strict audit requirements. Selecting the correct storage tier requires balancing provisioned IOPS, throughput limits, and monthly costs against your actual workload demands. Ultra disks support live scaling up to 20,000 IOPS without requiring virtual machine reboots for critical SQL databases. Premium SSD v2 delivers superior price-to-performance metrics for general enterprise applications. Standard SSDs adequately handle web servers and development environments, while standard HDDs remain the most economical choice for infrequently accessed backup repositories that rarely exceed 50 IOPS. First, evaluate your specific workload requirements and calculate the required IOPS to determine the appropriate storage tier. This assessment ensures you select a disk that precisely matches your application latency and throughput demands without over-provisioning expensive resources. Miscalculating these metrics often leads to unnecessary monthly billing spikes or severe performance bottlenecks during peak traffic windows. Documenting your baseline requirements prevents architectural drift and guarantees that every attached volume delivers consistent, predictable performance for production workloads. Here we create a managed disk using the exact Azure CLI syntax. Notice the SKU parameter set to Premium LRS, which selects the tier based on our performance assessment. We specify the resource group, name, size in gigabytes, and the storage type to ensure alignment with earlier workload requirements. Running this command incorrectly often results in mismatched disk configurations that fail validation checks. Verifying each parameter prevents deployment failures and guarantees the volume meets your application latency thresholds. Next, select the appropriate disk tier and configure encryption using customer-managed keys retrieved from Azure Key Vault. This configuration secures your data at rest by ensuring only authorized service principals can access the cryptographic keys. Failing to implement proper key management often results in compliance violations during security audits. Properly linking the encryption set prevents unauthorized data extraction while maintaining strict regulatory standards for financial and healthcare workloads deployed across multiple regions. This command creates a managed disk with customer-managed keys for encryption. The encryption type flag explicitly enables CMK mode, while the disk encryption set parameter points directly to your Key Vault resource identifier. Executing this correctly ensures data at rest remains protected using keys you fully control. Misconfiguring the resource ID often triggers deployment failures or leaves sensitive databases exposed. Verifying the encryption set prevents compliance breaches and guarantees secure storage for regulated workloads. Finally, implement automated backups using incremental snapshots and validate your virtual machine size limits to prevent severe throttling. This step ensures point-in-time recovery capabilities remain active, while guaranteeing the compute instance can actually support the provisioned IOPS of the attached disk. Ignoring VM capacity thresholds often causes unexpected performance degradation during peak processing windows. Validating these constraints prevents data loss and maintains consistent throughput for critical production applications running in your environment. Here we create a snapshot for reliable point-in-time backup. The As snapshot create command captures the exact disk state at this precise moment. Executing this operation provides a secure recovery baseline before applying major configuration changes. Always automate these snapshots through Azure backup policies to maintain disaster recovery readiness and meet strict compliance mandates. Skipping manual verification often leads to corrupted recovery points that fail during critical emergency restoration procedures. Let's check your understanding with a practical scenario. Which disk tier allows dynamic performance changes without restarting the virtual machine? Consider the options: Ultra Disk, Premium SSD v2, Standard SSD, or Standard HDD. Evaluate which tier supports live scaling of IOPS and throughput on the fly. Selecting the wrong tier during an exam often results in incorrect architecture recommendations that fail to meet strict latency requirements for production databases. A key principle to remember is that right-sizing your disks saves money and ensures consistent performance. Always match the disk tier precisely to the actual workload requirements. Over-provisioning wastes your monthly budget, while under-provisioning leads to severe IOPS throttling during peak processing windows. Use Azure Advisor reports to identify underutilized volumes and adjust accordingly. Ignoring these metrics often causes unexpected billing spikes that drain project budgets before deployment completion. Common pitfalls include ignoring IOPS limits, forgetting to format disks, and mixing storage tiers incorrectly. Every virtual machine size enforces a maximum IOPS limit. Attaching a high-performance disk to a small compute instance will inevitably cause severe throttling. Additionally, remember that Azure provides the raw block device, but you must initialize and format the volume in the operating system before it becomes usable. Overlooking this step often results in unmountable drives that fail application deployment checks. Premium and standard SSDs support disk bursting, which allows performance to exceed provisioned limits for short periods. When traffic spikes occur, the disk can burst up to 30 minutes to handle the load without requiring a permanent upgrade. This mechanism helps manage unexpected traffic surges efficiently while maintaining cost efficiency. Failing to monitor burst credits often leads to sudden performance degradation during critical database operations that require sustained high throughput for extended processing windows. We have covered managed disk fundamentals, compared disk tiers for performance needs, provisioned volumes using the Azure CLI, explored design best practices for security and backups, and examined common pitfalls like IOPS throttling. Managed disks simplify storage management while offering high availability and scalability for your applications. Mastering these concepts prevents architectural misconfigurations that frequently cause exam failures. Applying these techniques ensures your cloud infrastructure meets strict reliability standards while maintaining optimal cost efficiency across all workloads. For the AZ-305 exam, focus on selecting the correct disk tier based on workload requirements and understanding strict IOPS limits. Be prepared to identify when bursting is appropriate and recognize the critical importance of customer-managed keys for data security. Remember that managed disks handle storage account management automatically, simplifying your design decisions. Misinterpreting these configurations often leads to incorrect architecture recommendations that fail to meet compliance standards required for production environments. Imagine a massive library where books are stacked randomly on the floor, making retrieval nearly impossible. That is exactly what running production without structured storage looks like. Azure Data Lake Storage Gen 2 transforms chaotic object storage into a high-performance file system with instant directory operations. You must enable hierarchical namespace at creation to unlock POSIX access control lists and O1 renames. Without it, moving large datasets triggers costly copy and delete operations that blow up your egress costs and latency during peak analytics workloads. We will explore the core concepts of IDLS Gen 2 and its defining hierarchical namespace feature. You will design a lakehouse architecture using bronze, silver, and gold zones for effective data tiering. We will walk through implementation code for data ingestion using the ASCII command. Finally, we will cover best practices, security pitfalls involving our back versus POSIX ACLs, and exam-critical tips specifically aligned with the AZ-305 certification, objectives to prevent costly architecture mistakes. Azure Data Lake Storage Gen 2 is a specialized storage solution built directly on top of Azure Blob Storage Account v2. It combines massive scale with hierarchical file system semantics required for modern analytics. You must configure POSIX-compliant access control lists down to the file and directory level for granular security. Failing to implement these ACLs leaves your raw data exposed to unintended audience reads, while relying solely on storage account keys creates severe compliance violations during external audits. The defining feature of IDLS Gen 2 is the hierarchical namespace toggle within the storage account settings. In standard blob storage, folders are merely string prefixes in file names. IDLS Gen 2 establishes a true directory tree that enables O1 rename operations through metadata updates alone. This architecture prevents massive throughput bottlenecks during ETL pipelines and integrates seamlessly with Azure Databricks and Synapse Analytics for optimized query execution across petabyte-scale datasets. Standard blob storage handles general object retention efficiently, but completely lacks semantics and granular ICL enforcement. IDLS Gen 2 explicitly adds the hierarchical namespace to enable efficient directory operations and POSIX-compliant permissions. You must select this tier when deploying analytics workloads because standard containers cannot support parallel file processing. Choosing the wrong tier forces manual data migration scripts that introduce latency and increase operational overhead for your engineering team. Data flows through the lakehouse architecture across 3 distinct performance tiers. Raw sources land unprocessed information directly into the bronze zone for immediate ingestion. Pipelines then cleanse and validate that information into the silver zone before aggregating curated metrics into the gold zone. This structured progression guarantees strict data lineage and prevents downstream reporting failures caused by malformed or unvalidated source records entering production dashboards. We are actively designing the lakehouse architecture for your analytics environment. First, we ingest raw JSON and CSV payloads directly into the bronze zone to land unprocessed information from legacy SQL systems. You must configure lifecycle management rules immediately after this step to transition cold data to cool or archive tiers. Skipping this automation triggers unexpected egress fees and consumes valuable storage capacity during peak processing windows. Here is the implementation for Step 1 using the Python SDK. We initialize the Data Lake Service client using your primary account key. We access the file system client for the container, then get the directory client for our raw data path. We create a file client and append the raw data in 5 megabyte chunks. Finally, we flush the data to commit the file to the bronze zone safely. Next, we transform and validate the incoming payloads within your pipeline orchestration layer. We move from the bronze landing area to the silver zone, where data is deduplicated and converted to standard Parquet formats. You must enforce schema validation rules before this transition to prevent malformed rows from corrupting downstream aggregations and breaking scheduled reporting jobs across your organization. For Step 2, we simulate the transformation pipeline using memory-efficient streaming techniques. After appending the raw data, we flush it to commit the bronze file securely. Then we read that dataset, apply a cleaning operation in memory, and append the cleaned result to the silver directory. This pattern prevents out-of-memory exceptions when processing multi-gigabyte transaction logs during peak business hours. Finally, we curate the validated information for enterprise analytics consumption. We move processed records to the gold zone, aggregating them into optimized columnar structures for Power BI and Synapse workspaces. You must configure read-only access policies at this stage to prevent accidental data mutations. Bypassing these controls introduces version drift and compromises the accuracy of executive financial reports. For Step 3, we curate the final metrics directly into the gold zone directory. We access the curated path and create a summary file using append operations. We write aggregated data representing daily revenue totals and customer churn rates. This code demonstrates writing the curated output that BI tools will consume directly, ensuring consistent row counts across monthly reporting cycles. Data remains a dormant asset until it is properly discoverable and securely accessible across your engineering teams. Lake Gen2 ensures your lake functions as a structured foundation rather than an unmanaged dump site. You must implement consistent naming conventions and tag resources with cost center identifiers immediately. Neglecting these governance steps leads to orphan containers that inflate monthly invoices and complicate compliance audits for regulated industries. Let's check your understanding on storage account configuration. You are provisioning a new storage account for a heavy analytics workload using the Azure CLI. When must you enable the hierarchical namespace feature during the Azure Storage account create command? Remember that this setting is immutable after deployment, so missing the toggle forces complete data migration and causes significant project delays during certification scenarios. We covered the core concepts of Lake Gen2 and its mandatory hierarchical namespace toggle. You designed a lakehouse architecture utilizing bronze, silver, and gold zones for effective data tiering. We implemented SDK code for ingestion, transformation, and curation workflows. Finally, we discussed lifecycle management rules and deep nesting pitfalls that trigger performance degradation when querying millions of small files across distributed clusters. For the AZ-305 exam, remember that hierarchical namespace requires explicit enablement during account provisioning and cannot be modified later. Focus heavily on distinguishing RBAC for broad container access versus POSIX ACLs for granular file security. Also, recognize Lake Gen2 as the mandatory backend for Azure Databricks and Synapse Analytics to avoid performance penalty questions and ensure optimal query execution across your architecture diagrams. Imagine you are writing a check at a bank. You expect the teller to see that money is gone before handing it out to someone else. Now picture posting a photo on social media where you just want it to show up eventually. Azure Cosmos DB lives in this exact tension between banking precision and social speed. In this lesson, we will explore how Cosmos DB lets you choose the exact level of data freshness your application needs, balancing performance against reliability for your next certification exam. We will start by examining the CAP theorem trade-off that fundamentally drives these architectural choices. Then we will walk through the 5 specific consistency models available in Cosmos DB, including their exact latency ranges. Next, we will configure consistency levels using the Azure CLI and portal settings. Finally, we will cover common exam pitfalls regarding session tokens and strong consistency costs, so you can avoid costly misconfigurations during live deployments. In distributed systems, the CAP theorem states you can only guarantee 2 of 3 properties: consistency, availability, and partition tolerance. Cosmos DB must be partition tolerant to scale globally across regions, so we are strictly trading consistency against availability. Unlike traditional relational databases that offer only strong or eventual consistency, Cosmos DB provides a precise spectrum of 5 distinct models. This architectural flexibility allows you to pick the exact balance for each microservice feature, preventing unnecessary latency spikes during peak traffic. Strong consistency is the strictest model available in Azure Cosmos DB. It guarantees that every read operation will always return the most recent committed version of an item across all replicas. A client will never observe uncommitted or partial writes during high-throughput operations. This guarantee is absolutely essential for financial transactions or inventory management where stock levels must be exact, though it incurs higher latency and consumes more request units per second. Let's compare the key models side by side using practical exam scenarios. Strong consistency offers the highest guarantee but incurs the highest latency and cost across regions. Session consistency, which is the account default, ensures read-your-own writes within a single client session, balancing performance with predictability. Eventual consistency provides the lowest latency, but offers no ordering guarantees, making it ideal for non-critical analytics or counting social media likes where stale reads are acceptable. Now let's configure your consistency strategy using the as Cosmos DB update command or ARM templates. First, we set the account-level default consistency, which applies to all operations unless explicitly overridden by code. This establishes the baseline behavior for your entire Cosmos DB instance and dictates how replicas synchronize across geographic regions. Getting this initial setting wrong will force every single query to follow an unintended performance profile. Here is a JSON configuration snippet setting the account default to bounded staleness. We define the max staleness prefix, an interval to limit how far behind reads can lag, typically using values like 300 prefixes or 10 seconds. This sets the baseline for all requests that do not explicitly specify a different level, preventing unexpected data drift during critical business workflows. Next, we override consistency per request directly in your application code. The official SDK allows you to specify a different consistency level for individual operations, giving you granular control over specific reads or writes without changing the account default. This targeted approach prevents unnecessary latency spikes and keeps overall throughput costs predictable during high-volume data processing. In this CHash SDK example, we create an item request options object to override the account default for a specific read operation. We set the consistency level to session for this request, ensuring the client sees their own updates immediately, even if the account default is weaker. Failing to attach these explicit options will cause your application to silently fall back to the baseline behavior and miss critical updates. Finally, we manage session tokens for stateless IPIs running behind load balancers. When using session consistency, the SDK manages a session token internally within the client memory. If you are building a stateless web IPI, you must pass this token between the client and server via custom headers so the backend can maintain the session guarantee across different HTTP requests and multiple server instances. This CHash snippet shows how to handle session tokens in a stateless IPI architecture. We extract the session token from the incoming request headers and attach it to our SDK response options before executing the query. This ensures that subsequent requests from the same client maintain session consistency across different server instances, preventing duplicate reads or lost updates during peak traffic. Here is the exact data flow for session consistency during a typical write operation. The client sends a write request directly to the primary region endpoint. The primary processes the write and immediately updates the session token in memory. Secondary replicas catch up asynchronously within milliseconds. When the client reads next, the system returns the latest version associated with that session token, ensuring read-your-own writes without blocking other users. Let's check your understanding with a practical certification scenario. If your Cosmos DB account is configured with eventual consistency, can you request strong consistency for a specific read operation? The answer is absolutely no. You cannot request a consistency level stronger than what is configured for the account. Attempting to force a stricter guarantee will trigger a validation error and halt your deployment pipeline immediately. Remember this core principle for every architecture decision. Performance strictly follows consistency. The stronger the guarantee you request, the higher the latency and RU cost will be across all regions. Always ask if the user actually needs to see an update immediately, or if a slight delay is acceptable for better performance and lower infrastructure spending during peak load periods. We covered the CAP theorem trade-off and the 5 consistency models in Cosmos DB during this session. We configured account defaults and overrode them per request using the official SDK libraries. We managed session tokens for stateless IPIs to maintain consistency across distributed requests. Remember that strong consistency increases latency and cost, while session consistency offers the best balance for most web applications under heavy load. For the AZ-305 exam, focus heavily on the differences between consistency models and their specific use cases. Know that you cannot request a stronger consistency level than the account default configuration allows. Pay close attention to session token handling in stateless APIs when designing distributed systems. Strong consistency requires synchronous replication and increases RU consumption, so it is not the default choice for most applications. Imagine a massive library where every book is assigned to a specific librarian based on its unique ID number. When you need a book, you go directly to that librarian, and the process is instant. If every book went to the same librarian, they would be overwhelmed and you would wait forever. Azure Cosmos DB works exactly like this smart distribution system, using partitioning to ensure single-digit millisecond latency even under heavy load. Today, we will master the design decisions that keep your database fast and cost-effective. Here is our roadmap for this lesson. We will start by exploring the mechanics of partitioning and how data moves between logical and physical layers. Next, we will define request units and understand throughput distribution across Azure regions. Then, we will dive into a step-by-step guide for designing your partition key. After that, we will look at avoiding hot partitions and common pitfalls. Finally, we will wrap up with specific exam tips for the AZ-305 certification to ensure you pass on your first attempt. Cosmos DB relies on partitioning to scale horizontally across multiple regions. You must understand the difference between logical and physical partitions. A logical partition groups documents that share the same partition key value, while the physical partition is the actual storage unit managed by Azure, which can hold multiple logical partitions. When you write or read data, Cosmos uses the partition key to route your request directly to the correct physical node. This direct routing eliminates expensive cluster-wide scans and delivers consistent performance for production workloads. Let's define a critical term, request units. Cosmos DB measures the cost of operations in RUs, which abstract CPU, IOPS, and memory into a single currency. When you provision throughput, you reserve a specific number of RUs per second for your container using the Azure CLI or portal. This throughput is distributed equally across all physical partitions. If one partition holds most of your data, it will consume most of its allocated RUs, potentially causing throttling errors even if other partitions are idle. Here is how you define a container with a partition key using the NET SDK. We specify the path to the property that will serve as the key, in this case tenanted. The code creates the container if it does not exist and provisions 400 RUs per second via Azure CLI. This setup ensures that every document is routed based on its tenant identifier, isolating data per tenant and distributing the load across the cluster to prevent performance bottlenecks during peak traffic. Choosing the right partition key is the most important design decision for Azure Cosmos DB. High cardinality keys like ordered or deviceed ensure that data is spread evenly across many logical partitions. Low cardinality keys like status or country concentrate data into few partitions, creating hot spots. Always prefer high cardinality to avoid throughput bottlenecks and ensure your database can scale horizontally as demand grows, which directly impacts your monthly billing and application responsiveness under load. Let's visualize how a query flows through Cosmos DB. When you provide the partition key in your query, the request goes directly to the relevant physical partition. This is efficient and fast. However, if you omit the partition key, the database must send the query to every physical partition and merge the results. This cross-partition query consumes significantly more RUs and increases latency. So always scope your queries when possible to avoid unexpected throttling and excessive cloud costs. Now we will design your partition key step by step. First, analyze your access patterns to identify the most frequent query filters in your application code. This ensures your key aligns with how you retrieve data. Next, select a high cardinality property to distribute load evenly across partitions. Finally, enforce size limits to prevent any single logical partition from exceeding 20 GB. We will walk through each step with practical examples to secure your certification exam score. This code demonstrates analyzing access patterns by filtering on the partition key. The query uses a where clause to match the tenanted, ensuring the request is scoped to a single logical partition. This approach minimizes RU consumption and latency because Cosmos DB only searches the relevant data subset rather than scanning the entire container. Failing to scope queries correctly will drain your provisioned throughput and trigger 429 errors during critical business hours. Next, we select a high cardinality property. This means choosing a field with a wide range of unique values, such as ordered or deviced. Avoid low cardinality fields like status or country, which concentrate data and create hot partitions. High cardinality ensures that your throughput is distributed evenly, preventing any single partition from becoming a bottleneck. Misconfiguring this setting will cause write failures and degrade user experience across all connected clients. Here is a comparison of partition key choices for your Azure database. Using ordered as the key ensures every document goes to a unique logical partition, distributing load perfectly across the cluster. In contrast, using status concentrates data into few partitions, risking hot spots that exhaust allocated RUs. Always prefer high cardinality keys to maintain performance and avoid throttling errors under heavy load, which directly impacts your certification, exam score, and production reliability. Finally, enforce size limits to prevent hot partitions from growing too large. A single logical partition cannot exceed 20 GB of storage capacity. If your data grows beyond this limit, you will face write failures and service degradation. To avoid this, monitor partition sizes using Azure Monitor and adjust your key strategy if necessary. Synthetic keys can help distribute data further by combining properties to create unique identifiers that stay within strict size limits. This code shows how to create a synthetic key to enforce size limits effectively. By concatenating userid and timestamp, you generate unique identifiers that distribute data across partitions while preventing any single partition from growing too large. This technique helps maintain performance and avoids the 20 GB limit constraint. Skipping this step will cause write errors and force you to manually migrate data later, costing valuable time during your exam preparation. Remember this key principle for your Azure certification. Partitioning is the single most important decision you will make when building on Cosmos DB. It directly dictates both your performance metrics and your monthly cost structure. Design your partition key carefully to ensure horizontal scalability and efficient throughput distribution across all regions. Getting this wrong will result in unpredictable latency spikes and inflated cloud bills that fail audit requirements. Let's check your understanding with a practical scenario. What happens if you provision 1,000 RUs per second for a container, but one partition holds 90% of your data? You will hit a 429 too many requests error on that partition, even if the rest of the database is idle. This occurs because throughput is distributed equally across physical partitions, and the hot partition exhausts its allocated RUs during peak operations. To recap, Cosmos DB uses partitioning to scale horizontally, grouping data into logical partitions based on a defined key. You must design your partition key carefully to ensure high cardinality and avoid hot partitions that drain resources. Request units measure throughput, which is distributed across physical partitions in each region. Always scope queries to the partition key for efficiency and monitor sizes to stay under 20 GB for reliable production deployments. For the AZ-305 exam, focus heavily on partition key design and throughput management scenarios. You will likely encounter questions requiring you to choose the best partition key for a given workload using Azure CLI or PowerShell. Remember that keys cannot be changed after container creation, so initial design is critical. Also, know how to calculate RU consumption and identify hot partitions. Use the Capacity Planner tool in practice to estimate costs and performance accurately. Imagine you are a chef in a commercial kitchen. If you only have a paring knife, chopping vegetables is simple, but baking a cake is impossible. Azure Cosmos DB operates like that fully equipped workshop where every tool works seamlessly under one roof. You pick the IPI that fits your data recipe. On the AZ-305 exam, mastering this selection prevents costly rework and ensures you deploy the correct throughput model from day one, avoiding unexpected RU charge spikes during peak traffic. Here is our roadmap for mastering this topic. First, we will define what makes Cosmos DB unique as a multi-model service. Next, we will compare the 5 available IPIs using a structured reference table. Then, we will walk through a step-by-step strategy to choose the right IPI for your design. Finally, we will cover critical best practices and common pitfalls you must avoid on the AZ-305 exam, ensuring you never misconfigure throughput or select an incompatible data model during certification scenarios. Let us start with a key term you will see frequently on the certification exam. Multi-model means Cosmos DB supports multiple data models within a single account without requiring separate deployments. This is not just about storing JSON documents. It allows you to run core SQL, MongoDB, Cassandra, Gremlin, and table IPIs side by side. The architecture handles translation automatically, so you can pick the interface that matches your application needs without rewriting storage logic or risking data migration errors. The Core SQL IPI is the native interface for Cosmos DB and should be your default choice for most greenfield projects. It uses JSON as the storage format and offers rich indexing capabilities. The performance here is exceptional, often delivering up to 15 times better request unit efficiency compared to other IPIs. If you do not have a legacy driver dependency, the Core IPI gives you the deepest feature set, including Synapse link integration, preventing costly refactoring when analytics requirements inevitably emerge. Let us look at the full landscape of IPIs. The Core SQL IPI handles JSON documents for general microservices. The MongoDB IPI provides wire protocol compatibility, making it ideal for migrating existing Mongo workloads with minimal code changes. Cassandra is your go-to for wide column stores and time series data with heavy write throughput. Gremlin excels at graph structures for social networks and fraud detection. Finally, the Table IPI offers simple key-value storage for cost-effective, fast lookups in Azure Storage Explorer. Here is a practical example of the Core SQL IPI in action. We start by initializing the Cosmos client with our endpoint and key credentials from Azure Key Vault. Then we create a database and a container using the as Cosmos DB SQL container create command, specifying an ID for the partition key path. Finally, we define a user object with nested preferences and insert it into the container, demonstrating how straightforward JSON storage becomes while preventing accidental global distribution misconfigurations. Now let us build a strategy for selecting the right IPI. We will use a cumulative approach to walk through the decision process. First, we must analyze the data structure of your application. This sets the foundation for everything else, ensuring you avoid costly schema migrations later and align your partition key strategy with actual read-write patterns before provisioning any resources in the Azure portal. To analyze data structure, look at how your entities relate in production. If you have flat objects with nested properties, the core SQL IPI is a strong fit. This code creates a user profile document with a partition key and nested settings. The structure here is hierarchical but self-contained, which maps perfectly to JSON storage without needing complex joins, preventing query latency spikes when scaling beyond 20,000 requests per second. With the data structure analyzed, we move to the second step. Next, evaluate your query patterns carefully. You must choose an IPI based on how you need to traverse and retrieve data, not just what you know from previous projects. Selecting the wrong interface here will force expensive application rewrites and cause severe throttling when your workload exceeds standard RU allocations during peak business hours. When evaluating query patterns, consider if you need to traverse complex relationships across multiple entities. This gremlin example finds friends of friends for a specific user identifier using the gv has id user 123 out knows in knows traversal command. The graph IPI follows edges and deduplicates results efficiently. If your application relies heavily on this kind of relationship exploration, the core SQL IPI would struggle, making Gremlin the necessary choice to avoid query timeouts. We have analyzed structure and queries. Now for the final step. Finally, check ecosystem needs and scaling requirements carefully. This includes legacy driver dependencies and analytical workloads like Synapse Link. Ignoring these factors will force you to decommission entire clusters later, wasting budget and causing unexpected downtime when your application outgrows the initial capacity planning assumptions made during the design phase. For ecosystem needs, consider Synapse Link and partition key distribution strategies. This configuration enables Synapse Link for near real-time analytics on the core SQL IPI. It points to a file store for analytical workloads without impacting transactional performance. Always verify that your chosen IPI supports these features and that your partition key strategy prevents hot partitions, which could otherwise spike latency and trigger automatic service throttling during high-volume events. Here is a pro tip for your design process that examiners love to test. When you are unsure which IPI fits best, prototype aggressively. Cosmos DB allows multiple containers in one account. Create a small subset of data in both the core SQL and the target IPI to compare performance and developer experience before committing. Skipping this validation step often leads to costly refactoring when production traffic reveals unexpected query bottlenecks. Let us check your understanding with a classic certification scenario. You are designing a social network application that needs to find mutual friends and detect fraud based on complex relationships. Which IPI should you select? Think about the query patterns and data structure required for graph traversal. Choosing core SQL here will cause severe performance degradation, so always match the workload to Gremlin for optimal edge querying. Let us visualize the Synapse Link advantage directly in the Azure portal. When you write transactions, they go to the primary write store using standard SQL queries. Simultaneously, Synapse Link replicates the data to an analytics store with a typical delay of 3 minutes or less. This allows you to run analytical queries on near real-time data without impacting your transactional performance, preventing dashboard lag during critical reporting windows. We have covered the essentials of IPI selection for your architecture. Remember that Cosmos DB offers multi-model flexibility, allowing you to choose the right tool for the job. The core SQL IPI is usually the default choice due to its maturity and performance. Compatibility IPIs like MongoDB or Gremlin are best for migrating existing workloads or specific data models. Always prioritize partition keys and indexing to ensure scalability and avoid unexpected RU charge spikes. For the exam, focus on these critical points outlined in the official AZ-305 blueprint. You will often be asked to select an IPI based on a scenario description. Look for keywords like graph, relationships, or social to identify gremlin. Watch out for the migrator's trap. Do not choose an IPI just because you have legacy code if it does not fit the long-term data model. Finally, remember that partition key selection is paramount. A poor choice will cause hot partitions regardless of the IPI. Imagine a massive logistics warehouse where packages arrive at lightning speed. If every package lands on the same shelf, that shelf collapses under the weight while others sit empty. This is exactly what happens when you design storage without thinking about distribution. In this lesson, we will master Azure Table and Queue Storage to build systems that scale effortlessly. You will learn to configure partition keys for predictable throughput, avoiding hot partition errors that crash production applications during traffic spikes. Here is our roadmap for mastering these services. We begin by exploring table storage fundamentals and why it outperforms traditional SQL for petabyte-scale telemetry. Next, we dive into partition key strategies, which directly dictate your provisioned throughput limits. Then we examine queue storage for decoupling microservices using standard REST endpoints. Finally, we cover critical exam pitfalls regarding message visibility timeouts to ensure your architectures pass certification and handle real-world failures gracefully. Let's define our primary tool, Azure Table Storage. This is a NoSQL key attribute store designed for massive scale and low-cost storage of structured, non-relational data. Unlike SQL databases, it has no fixed schema, meaning each row or entity can hold different properties. You use it when you need petabyte-scale capacity for IoT telemetry or user profiles where complex joins are unnecessary. For example, storing sensor readings from thousands of Azure IoT Hub devices requires flexible schemas and rapid ingestion. Mastering this avoids costly migration projects later. Table storage shines when you need to handle millions of operations per second across distributed nodes. It provides low-latency access and automatically scales, but performance relies entirely on your data distribution strategy. If you design poorly, you create hot partitions where a single storage node gets overwhelmed while others idle. For instance, using a static partition key for all user logs will trigger throttling errors during peak hours. We will fix this with smart partitioning to guarantee consistent sub-second response times. Now let's look at the most critical design pattern for tables. We will walk through a three-step process to ensure your data is distributed perfectly across storage nodes. First, we analyze query patterns to understand how data flows through your application logic. This blackboard will build cumulatively as we add each step. You must map every read operation before writing code, because misaligned queries force full table scans that consume unnecessary request units and degrade overall system throughput. This code defines a device entity for table storage using the Azure CLI SDK. Notice the partition key and row key properties clearly defined in the class. The partition key groups related entities on the same server node, while the row key ensures uniqueness within that specific partition. We structure this entity based on how we will query it, not how it looks in a normalized model. You must align these keys with your actual IPI calls to prevent latency spikes and ensure efficient data retrieval during peak loads. With the pattern in mind, we add our second step, selecting a high cardinality partition key for every write operation. This ensures writes spread across multiple storage nodes instead of hitting one server sequentially. We actively avoid monotonic values like sequential timestamps or auto-incrementing integers that cause hot partitions. You should append a random suffix or use tenant identifiers to distribute load evenly, because concentrated writes will trigger service throttling and crash your ingestion pipeline during traffic surges. Here we see the practical application of partitioning in a multi-tenant SaaS environment. We use tenanted as the partition key to distribute load across distinct customer bases. This prevents one tenant's traffic spike from degrading performance for others sharing the same storage account. The row key remains unique within that tenant's partition, allowing efficient lookups via standard REST calls. You must implement this strategy immediately, because failing to isolate workloads will cause cascading failures when a single client exceeds their provisioned throughput limits. Finally, we complete the design by assigning a meaningful row key that supports your exact query patterns. The row key sorts data within the partition and enables efficient range queries across your dataset. We combine static identifiers with sequence numbers to maintain chronological order without creating hot partitions. You must carefully calculate these composite keys before deployment, because poorly ordered sequences force inefficient scans that consume excess request units and delay critical reporting dashboards. This example shows a robust row key design for an IoT telemetry pipeline. We combine the device identifier with a sequence number to support precise chronological ordering. This approach keeps data organized for queries while avoiding the monotonic timestamp pitfall that causes severe performance bottlenecks in distributed systems. You should implement this pattern immediately, because sequential writes will saturate a single storage node and trigger throttling errors that disrupt your real-time monitoring alerts. Let's compare table storage against queue storage to clarify their distinct architectural roles. Tables excel at key-value lookups and structured data with high scale, supporting flexible schemas for rapid ingestion. Queues specialize in message buffering and asynchronous decoupling between microservices using standard HTTP endpoints. Understanding this distinction prevents you from forcing relational modeling into the wrong storage type. You must choose queues for background job processing, because misusing tables for messaging will cause deadlocks and severely degrade your application latency. Queue storage follows a precise workflow to ensure reliable message delivery across distributed workers. The producer adds messages to the queue using standard HTTP post requests. A consumer retrieves them and sets a visibility timeout, hiding the message from other active workers. After processing completes successfully, the consumer explicitly deletes the message. If the consumer crashes, the default 30-second timeout expires and another worker picks it up, preventing data loss during infrastructure failures. This code demonstrates the queue processing workflow using the Azure SDK for Python. We receive messages in batches and loop through each item sequentially. Crucially, we delete the message only after successful database writes and logging operations complete. This ensures strict idempotency and prevents data loss if a worker process crashes unexpectedly. You must implement this exact pattern, because failing to handle duplicates will cause duplicate invoices and corrupt your financial records during peak processing windows. Remember this principle as you design distributed systems. Partition keys determine performance, and idempotency ensures reliability across every service boundary. Never force relational joins into table storage. If you need complex relationships, choose Cosmos DB or Azure SQL instead. Design for failure from the start by implementing retry policies with exponential backoff. You must follow these rules immediately, because ignoring them will cause cascading timeouts and severely degrade your production environment during unexpected network interruptions. Let's check your understanding with a quick certification scenario. Which key determines the exact storage node location for a table storage entity? Is it the row key, the partition key, or the entity ID? Think about how data is distributed across nodes to answer this correctly. The correct answer is the partition key, because it dictates physical routing and throughput allocation. Mastering this concept prevents you from accidentally creating hot partitions that throttle your production workloads during peak traffic hours. Avoid these common pitfalls to pass the exam and build robust cloud systems. For tables, never use monotonic timestamps as partition keys. This creates hot partitions that bottleneck performance and trigger throttling errors. For queues, implement idempotency to handle duplicate messages gracefully during worker restarts. Also, move large blobs to blob storage and store only URLs in table entities to keep query latency below 100 milliseconds. You must apply these rules immediately, because skipping them will inflate your monthly storage costs and degrade user experience. We covered the essentials of table and queue storage design for modern cloud architectures. Tables provide massive scale for key-value data, but require careful partition key design to avoid hot spots that throttle ingestion. Queues decouple services through asynchronous message buffering with guaranteed at least once delivery mechanisms. Always design for failure, implement idempotency, and choose the right tool for your access patterns. You must master these concepts immediately, because misconfigured storage layers will cause data corruption and severely impact your certification exam score. For the AZ-305 exam, focus on these key architectural points. You must know that table storage is a NoSQL key attribute store, not a relational database. Partition key design is critical for performance and distribution across storage nodes. Queue storage guarantees at least once delivery, requiring idempotent consumers to prevent duplicate processing. Avoid complex joins in tables. Use Cosmos DB instead for graph relationships. Master these distinctions immediately, because confusing these services will cost you valuable points on the practical design scenarios. Imagine you are shipping a container of gold across the ocean. You do not just lock the door. You use armored trucks, encrypted manifests, and armed guards at every checkpoint. In NoSQL databases, your data faces similar risks across distributed networks. Storage security ensures that even if an attacker intercepts traffic or steals a disk, the information remains useless. For Azure Cosmos DB, you must enable customer-managed keys alongside TLS 1.3 encryption. Let us design a defense-in-depth strategy for your non-relational storage. Here is what we will cover in this lesson. We will start by mapping the layers of encryption and where they apply to your NoSQL architecture. Next, we will dive into field-level encryption as the gold standard for sensitive data. Then we will look at key management best practices using Azure Key Vault. Finally, we will review common pitfalls that compromise storage security. Mastering these concepts prevents accidental exposure during compliance audits and ensures you pass the certification exam with confidence. Securing NoSQL data requires a multi-layered approach. First, encryption at rest protects physical disks and snapshots using transparent data encryption or provider-level tools like Azure Storage Service Encryption. Second, encryption in transit uses TLS 1.2 or higher to prevent man-in-the-middle attacks during network transfers. Finally, identity and access management ensures only authorized services can decrypt and read the data. Together, these layers create a robust defense that blocks unauthorized access even if your network perimeter is breached. Field-level encryption is the practice of encrypting specific data fields within a document before they are written to the database. Unlike disk-level encryption, which hides the entire file, FLE ensures that sensitive values like SSNs or credit card numbers remain encrypted even inside the database engine. This is critical because it prevents administrators and compromised database processes from accessing plaintext data. You must configure this directly in your application code to meet strict compliance standards and avoid massive regulatory fines. Let's look at a MongoDB implementation of field-level encryption using the Node.js driver. Here we define a schema that marks the SSN field for encryption with a deterministic algorithm. The client configuration points to a key vault namespace and specifies the KMS provider details. When you insert a document, the driver automatically encrypts the SSN field before it hits the storage layer. This prevents accidental logging of plaintext credentials and satisfies audit requirements for sensitive healthcare data. Understanding the differences between encryption strategies helps you choose the right tool for each data type. At-rest encryption is managed by the provider and requires zero code changes, making it easy to implement but less granular. In-transit encryption protects network traffic but relies on secure endpoints. Field-level encryption offers the highest security by encrypting specific fields client-side, though it requires schema modifications and KMS integration. Selecting the wrong method will cause performance bottlenecks during peak transaction loads. Now let's walk through the steps to secure your NoSQL environment. We will start by enabling encryption at the storage layer, then move to implementing client-side field encryption, and finally enforce strict access controls. This sequence ensures that every layer of your architecture is protected against modern threats. You must follow this exact order because skipping storage encryption leaves raw bytes exposed during routine maintenance operations. For the first step, you enable transparent data encryption through your cloud provider's console, or CLI. This action automatically encrypts all underlying storage volumes and snapshots without requiring code changes in your application. It is the foundational layer that protects against physical disk theft or unauthorized snapshot access. Run the as-cosmosdb update command with the encryption key source parameter to verify your configuration meets compliance standards immediately. Next, we add client-side field encryption to protect sensitive data fields. This requires defining an encryption schema in your application code and configuring the database client to use a key management service. The driver will now intercept writes and encrypt specific fields before they reach the storage layer. You must test this thoroughly because misconfigured schemas will cause immediate query failures across your production environment. In this code snippet, we define a schema that marks the SSN field for deterministic encryption. The client configuration links to a key vault namespace and specifies the KMS provider. This setup ensures that the SSN is encrypted before it leaves the application, while still allowing equality queries on the encrypted field. You must allocate at least 5 milliseconds of latency per operation because cryptographic hashing adds measurable overhead to your request pipeline. Finally, we enforce least privilege access control through IAM. Encryption is useless if an attacker has the keys to decrypt it. By configuring strict roles and permissions, you ensure that only authorized services can access specific data collections. This step completes your defense-in-depth strategy. You must assign exactly read-only scopes to background workers to prevent accidental data deletion during routine maintenance cycles. Here we configure IAM policies to restrict database access. The policy grants read-only permissions to a specific microservice role and denies all write operations. This ensures that even if a service is compromised, the attacker cannot modify or delete critical data. Always review audit logs regularly to verify these controls. Configure the exact role ID for Cosmos DB built-in contributors to block unauthorized schema modifications during peak traffic windows. Remember this principle: defense in depth is not optional. You must combine encryption, access controls, and monitoring to protect your data effectively. Relying on a single security layer creates immediate vulnerabilities that compliance auditors will flag during routine assessments. Always implement overlapping safeguards to guarantee continuous protection across all database endpoints and prevent costly breach penalties. Let's check your understanding. If you need to perform equality queries on an encrypted field, which encryption algorithm should you use? A random encryption, B. Deterministic encryption, C. Field-level encryption, D. Transparent data encryption. Choose carefully because selecting the correct algorithm directly impacts query performance and determines whether your application can successfully retrieve records during high-throughput operations. To summarize, we covered the essential layers of storage security: encryption at rest, in transit, and field level. We implemented a MongoDB FLE configuration to protect sensitive fields client-side. We also walked through securing your environment by enabling storage encryption, configuring field encryption, and enforcing IAM controls. These steps ensure your NoSQL data remains secure against modern threats. Master this workflow to confidently handle compliance scenarios on your certification exam. For the AZ-305 exam, focus on key management and compliance. You will likely encounter scenarios where you must choose between encryption strategies based on data sensitivity and performance requirements. Remember that field-level encryption provides the highest security but requires more application code. Always select a centralized KMS for key rotation and audit capabilities. Practice identifying the correct IAM policies for specific microservice roles to avoid losing points on scenario-based questions. Imagine you're driving a heavy truck with a compact four-cylinder engine up a steep mountain pass. That is exactly what happens when you mismatch Azure SQL Database service tiers to your actual workload characteristics. Picking the wrong tier either burns money on unused compute or triggers painful performance failures during peak traffic. In this lesson, we will learn how to match your specific transaction requirements to the correct provisioning strategy and scale confidently. We will cover 4 essential areas to master Azure SQL database sizing. First, we compare the vCore and DTU purchasing models, highlighting why Microsoft deprecated legacy options. Next, we examine general-purpose, business-critical, and hyperscale tiers with specific latency thresholds. Then, we execute actual Azure CLI commands to provision a server and database. Finally, we discuss scaling strategies and retry logic to prevent application timeouts during maintenance windows. Azure SQL Database offers 2 purchasing models, but you must prioritize the vCore model for nearly every modern workload. The vCore model decouples compute from storage, giving you independent control over performance and capacity. This flexibility aligns closely with on-premises SQL Server behavior and supports all new Azure SQL innovations. The older DTU model bundles metrics into a single number, which restricts granular tuning and often leads to over-provisioning costs during peak traffic. Let's define a key term you will encounter frequently on the certification exam: vCore. A vCore represents a virtual processor core allocated to your database instance. In the vCore model, you select the exact number of vCores based on your application transaction requirements. This direct mapping allows you to predict performance more accurately than with bundled metrics, making it easier to right-size your infrastructure and avoid painful throttling errors during sudden traffic spikes. The vCore model is divided into 3 distinct service tiers, each optimized for different workload patterns. General Purpose offers a balanced approach with remote storage, suitable for most business applications. Business Critical uses local SSDs to deliver ultra-low latency and high availability for transaction-heavy systems. Hyperscale supports massive databases up to 100 terabytes with distributed storage for rapid scaling, preventing backup windows from blocking production deployments. Understanding the architecture helps you choose the right tier for your specific SLI requirements. In general purpose, compute nodes connect to remote storage over a network, which introduces slight latency but offers flexibility. Business-critical places storage directly on local SSDs attached to the compute node, minimizing read and write delays. Hyperscale distributes data across multiple storage nodes, allowing fast backups and restores regardless of database size. Now let's walk through the practical workflow for provisioning a database using automated scripts. We will use the Azure CLI to automate this process, which is essential for infrastructure as code workflows and reproducible environments. First, we create the resource group and SQL Server to establish the hosting environment, ensuring you avoid manual configuration drift across development and production subscriptions. First, provision the resource group and SQL Server using the AZ-SQL Server. Create command to establish the hosting environment. We define the region as East US and set administrative credentials for the server. Adding tags helps identify this resource in your subscription for cost tracking, while preventing accidental deployment of sensitive workloads into unmonitored regions. Next, we create the database instance and specify the service tier. This step defines your performance baseline by selecting the general purpose tier with 2 vCores. You can adjust the vCore count based on your expected load to avoid over-provisioning, which directly impacts your monthly billing cycle and operational expenditure budgets. Next, create the database instance using the AZ-SQL DB. Create command and specify the general purpose tier with 2 vCores to define your performance baseline. The payload includes the resource group, server name, and a sample database for initial testing. This configuration balances cost and capability for standard workloads, preventing unexpected throttling when concurrent user sessions exceed memory limits. Finally, we scale the database dynamically to handle increased load. Azure SQL allows you to change the vCore count without downtime, though brief connection drops may occur during failover. Scaling up ensures your application maintains performance as traffic grows, while preventing cascading failures across dependent microservices and API endpoints. Finally, scale the database capacity up to 4 vCores using the AZ-SQL DB update command on demand to handle increased load without downtime. The request modifies the service object to reflect the new vCore count. This dynamic scaling ensures your infrastructure adapts to workload changes efficiently, while requiring careful monitoring of CPU thresholds to trigger automated scaling policies. Remember this principle: scale up only when metrics demand it. Monitoring CPU and I/O usage helps you identify when a tier upgrade is necessary, preventing unnecessary costs. Always design your application with retry logic to handle transient errors during scaling operations, which avoids catastrophic data loss if connection pools exhaust unexpectedly. Let's check your understanding. Which service tier would you choose for a high-frequency financial trading platform requiring millisecond latency? The answer is business critical, as it uses local SSDs to minimize read and write delays, ensuring the low latency performance required for real-time transactions. Choosing incorrectly will trigger SLI breaches and fail compliance audits. To recap, we compared the vCore and DTU models, emphasizing vCore for its flexibility. We explored general purpose, business critical, and hyperscale tiers, each suited for different workload patterns. You learned the provisioning workflow using AZ-SQL commands and how to scale databases dynamically. Finally, we highlighted the importance of monitoring and retry logic for resilience, which prevents production outages during peak hours. For the AZ-305 exam, focus on selecting the correct tier based on workload characteristics. You may be asked to identify when to use business critical versus general purpose based on latency requirements. Remember that vCore is the preferred model and understand how scaling affects connection resilience. Practice as-SQL DB commands and recognize the impact of service objectives on performance to avoid costly misconfigurations. Imagine moving a massive, custom-built factory to a new city. You cannot simply drop it on the curb. You need a reinforced concrete foundation and specific zoning permits to keep it running safely. Azure SQL Managed Instance acts as that exact foundation, letting you lift legacy SQL Server workloads into Microsoft Azure without rewriting code. This approach prevents costly downtime while giving you automated patching and native VNet integration, which is exactly what the AZ-305 exam expects for hybrid database transitions. In this lesson, we will explore the architectural design of SQL Managed Instance. We will cover strict network requirements like dedicated 26 subnets and custom user-defined routes, compare general-purpose versus business-critical storage tiers to optimize IOPS, walk through complete provisioning using bicep templates, and review targeted best practices specifically aligned with the AZ-305 exam blueprint to ensure you pass on your first attempt. SQL Managed Instance is a platform as a service offering that bridges the gap between Azure SQL Database and SQL on virtual machines. It provides full compatibility with the SQL Server engine, supporting features like cross-database queries, SQL agent jobs, and CLR integration. This makes it the ideal choice for organizations migrating on-premises workloads, but failing to configure proper network isolation can cause unexpected connectivity failures during peak transaction hours. Let's define a key term you will encounter frequently on the certification exam. A managed instance is a logical grouping of SQL Server instances that share the same virtual network and subnet. It abstracts the underlying infrastructure management, handling patching and backups automatically, while exposing a standard TCP endpoint for your applications to connect. Misconfiguring this endpoint will immediately break application connectivity and trigger critical alert escalations. Network design is critical for SQL Managed Instance. Unlike Azure SQL Database, which uses public endpoints by default, MI lives strictly inside your virtual network. You must allocate a dedicated subnet with no other resources and configure user-defined routes to ensure the instance can communicate with Azure Management Services for patching and monitoring. Skipping this routing step will completely block service updates and leave your database vulnerable to unpatched security flaws. Let's design the instance step by step on the whiteboard. First, you must isolate the instance in a dedicated subnet and configure routing to ensure management access. You will need to reserve at least 20 IP addresses within that subnet, because Azure requires extra addresses for internal load balancers and storage controllers. Failing to meet this minimum count will immediately trigger a provisioning validation error. Here is the bicep code to provision the network foundation. We define a resource group and a virtual network with a subnet specifically for the managed instance. The subnet ID is then referenced in the instance properties, ensuring isolation and correct routing configuration. This exact structure prevents IP conflicts and guarantees that your database traffic flows through the intended private endpoints without leaking into public space. Next, we select the compute and storage tier based on workload requirements. You must choose between general purpose for cost efficiency or business critical for low latency. Additionally, Apply Azure Hybrid Benefit if you have existing licenses with software assurance to reduce costs. Selecting the wrong tier will cause severe query timeouts during peak processing windows and unnecessarily inflate your monthly cloud spend. This bicep snippet completes the provisioning by defining the managed instance itself. We set the SKU to general purpose Gen 5 with 8 vCores and 512 GB storage. The license type is explicitly set to base price, indicating we are using Azure Hybrid Benefit to leverage our existing on-premises licenses. Forgetting to declare this parameter will double your licensing costs and trigger unexpected billing alerts during the first month. When comparing options, SQL Managed Instance sits between Azure SQL Database and SQL on VM. MI offers full engine compatibility and VNet isolation, making it superior for lift-and-shift migrations. SQL Database is serverless and limited in features, while SQL on VM requires you to manage the OS and patching overhead. Choosing the wrong service will either restrict your T-SQL capabilities or force you to maintain unnecessary infrastructure tasks. Storage performance varies strictly by tier. General purpose uses remote Azure Premium Storage, where IOPS scale linearly with storage size up to 2 terabytes. Business Critical uses local NVMe SSDs for significantly lower latency and higher throughput. If you hit a performance ceiling in general purpose, increasing storage size is often the most effective scaling strategy before upgrading compute resources. Let's check your understanding with a quick design challenge. You are designing a solution for a legacy application requiring SQL agent jobs and cross-database queries. The application must be isolated in a VNet. Which service should you choose? Consider the compatibility and network requirements we discussed, because selecting an incompatible option will break scheduled maintenance tasks and violate strict compliance isolation policies. Performance tuning involves actively managing TempDB contention. In SQL Managed Instance, the engine is pre-configured, but you should minimize TempDB usage by using local variables instead of temporary tables. Monitor I/O statistics regularly to identify bottlenecks and adjust storage size or compute resources accordingly. Ignoring these metrics will cause severe lock waits and dramatically degrade query response times during heavy reporting cycles. Remember this principle clearly. Leverage the PaaS nature of the service to drastically reduce total cost of ownership. Automated backups, high availability, and patching allow you to focus on application value rather than infrastructure maintenance. Neglecting these built-in capabilities will force your team into manual operational overhead and increase the risk of unplanned database outages during critical business hours. Use this T-SQL query to monitor storage performance directly. It retrieves I/O stall times and read-write counts for all databases using the SIS, DMEO virtual file, stats dynamic management view. Analyze these metrics to identify which files are causing latency and determine if you need to adjust your storage allocation. Failing to track these thresholds will result in silent performance degradation that eventually breaks production workloads. We covered the core aspects of SQL Managed Instance design today. You learned about strict VNet isolation and subnet requirements, compared storage tiers for performance optimization, provisioned instances using Bicep with hybrid benefit, and reviewed best practices for monitoring and maintenance. Mastering these specific configurations will directly prepare you for complex scenario questions on the certification exam. For the AZ-305 exam, focus heavily on distinguishing between SQL database and managed instance scenarios. Expect questions on VNet configuration, subnet isolation, and storage tier selection. Remember that MI supports legacy features like SQL Agent and CLR, which are not available in SQL Database. Misunderstanding these boundaries will cause you to select incorrect architecture options and lose valuable points on performance tuning questions. Imagine you are opening a restaurant without professional equipment and staff. That is exactly what running production workloads on raw virtual machines looks like. In Azure, managed database services act as your fully equipped commercial kitchen, where engineering teams handle patching, backups, and hardware maintenance. This approach removes infrastructure overhead so you can focus entirely on application logic. You will avoid costly downtime and ensure your data layer remains compliant with enterprise security standards throughout its lifecycle. Today, we will examine the architecture behind Azure Database for MySQL and Postgres flexible servers. You will learn to deploy production instances using the MySQL flexible server, create command with precise SKU selections. We will configure private link endpoints and Entra ID authentication to lock down access. Then, we will tune performance metrics and establish high availability policies. Mastering these steps prevents unexpected read-only states and ensures you pass the AZ-305 design exam on your first attempt. These relational engines automatically handle failover across availability zones and manage storage, scaling independently from compute cores. You gain built-in encryption at rest using platform-managed keys and in transit via TLS 1.2 protocols. The platform executes daily automated backups with 7-day retention windows and applies security patches during your chosen maintenance window. Skipping these configurations risks data loss during sudden traffic spikes and leaves your application vulnerable to unpatched vulnerabilities that examiners frequently test. The flexible server model replaces the legacy single-server architecture entirely and provides granular control over maintenance scheduling and high availability topologies. You can configure zone-redundant deployments and integrate Entra ID for passwordless authentication directly into the connection string. Targeting this modern baseline ensures you access latest performance improvements and avoids deprecated feature limitations that consistently appear on certification assessments requiring current architectural knowledge. We will execute 3 precise steps to guarantee your environment meets enterprise standards from deployment day. First, provision the compute and storage tier in your designated region. Second, enforce strict network isolation using private link endpoints. Third, configure identity-based access control to replace legacy password authentication. Following this exact sequence prevents misconfigured firewall rules and ensures your database passes security audits without requiring emergency hotfixes later. Run as group, create to establish your target location first. Then execute as MySQL flexible server, create with the Gen2 SKU, and set storage to 50 GB. Specify a secure administrator password and enable backup retention for 7 days. Skipping precise SKU selection causes performance bottlenecks during peak traffic, while neglecting backup retention guarantees data loss if accidental deletion occurs during routine maintenance operations. After provisioning completes, immediately restrict public network access to disabled state. Configure private link endpoints to route all client traffic through your virtual network subnets. Switch authentication methods to Entra ID and disable legacy password credentials entirely. Failing to isolate network pathways exposes sensitive records to untrusted internet routes and creates compliance violations that trigger immediate audit failures during certification scenarios. Instantiate your client object using the fully qualified server name ending in MySQL Database, Azure. Pass your admin username and password through environment variables rather than hard-coding them directly. Explicitly set SSL-ca to point at the downloaded DigiCert certificate file and enforce verify mode as CERT required. Bypassing certificate verification allows man-in-the-middle interception and completely defeats encryption requirements mandated by enterprise security policies. You must enable zone redundancy to distribute database instances across 3 distinct availability zones within your region. Configure storage auto-grow to increase capacity automatically when usage approaches 90% of the allocated limit. Define a 7-day automated backup retention policy to maintain point-in-time recovery options. Ignoring these settings causes immediate read-only lockouts during traffic surges and eliminates disaster recovery capabilities required for production workloads. Specify HA mode as zone redundant to distribute replicas across separate physical data centers within the same geographic region. Set storage auto-grow to enabled and configure backup retention days to 7 for continuous data protection. These parameters prevent sudden read-only states when transaction logs exceed allocated disk space. Misconfigured YAML files frequently cause deployment failures during automated pipeline executions and trigger unexpected service interruptions during peak business hours. Select MySQL for standard web applications requiring broad ecosystem compatibility and straightforward relational queries. Choose Postgres when you need advanced JSON-B storage capabilities, complex window functions, or PostGIS extensions for spatial mapping operations. Understanding these architectural differences prevents performance degradation during heavy analytical workloads and ensures you select the correct engine that matches specific certification scenario requirements accurately. Analyze slow query logs regularly using the explain analyze command to identify missing indexes and inefficient join operations. Deploy PG bouncer connection pooling to manage persistent database sessions efficiently without exhausting available connection limits. Failing to monitor query execution plans causes CPU throttling during peak hours and creates cascading timeouts that directly impact end-user experience across your entire application stack. Security functions as the absolute foundation of your data architecture rather than an optional add-on component. You must prioritize private link network isolation and Entra ID authentication to protect sensitive customer information from unauthorized access. Neglecting these baseline controls creates critical compliance gaps that trigger immediate audit failures and expose your infrastructure to preventable security breaches during production operations. Consider which deployment model meets modern standards for new development projects and why the alternative architecture is being completely retired. Evaluate how flexible server provides granular maintenance scheduling and zone redundancy compared to legacy single server limitations. Understanding these distinctions prevents architectural misconfigurations during certification scenarios and ensures you select the correct baseline for long-term enterprise support requirements. Configure geo-replication to maintain read replicas across separate Azure regions for complete regional disaster recovery coverage. The primary database synchronizes transaction logs asynchronously to the secondary region while maintaining continuous backup operations. This architecture allows manual or automatic failover during extended outages and prevents permanent data loss if an entire geographic zone experiences unexpected infrastructure failure. Schedule maintenance windows during off-peak hours to prevent unexpected service restarts during critical business operations. Monitor the storage used metric continuously and configure auto-grow policies before reaching 90% capacity utilization. Relying on manual scaling decisions causes sudden read-only lockouts when transaction logs exceed allocated disk space and creates cascading application failures that directly impact end-user availability. We examined managed service architecture and the flexible server deployment model for production environments. You learned to provision instances using Azure CLI commands, enforce network isolation with private link endpoints, and configure identity authentication. Remember to enable zone redundancy, monitor storage metrics continuously, and optimize query performance to maintain enterprise-grade resilience throughout your application lifecycle. Focus on differentiating flexible server capabilities from legacy single-server limitations during certification scenarios. Master high-availability configurations, including zone redundancy and geo-replication failover procedures. Understand private link networking requirements and Entra ID authentication flows thoroughly. Identify performance bottlenecks using Query Performance Insight and recommend appropriate scaling strategies based on actual Azure Monitor metrics to pass the exam confidently. Imagine a popular coffee shop with only one espresso machine. As the morning rush hits, customers wait in line because that single machine is maxed out. You have two choices: buy a bigger, faster machine to handle more cups per minute, or open a second shop next door to split the crowd. Database scaling works exactly this way. Mastering these patterns is critical for the AZ-305 exam and prevents catastrophic downtime when traffic spikes unexpectedly. We will start by defining vertical scaling and reviewing a practical Azure database for Postgres configuration. Next, we will examine horizontal strategies like red replicas and sharding across multiple regions. Then, we will compare these approaches side by side to understand their trade-offs. Finally, we will walk through a step-by-step implementation strategy using the as-SQL DB command to help you make the right architectural decisions for your exams and real-world projects without causing unplanned service interruptions. Vertical scaling, often called scaling up, involves increasing the compute and memory resources of a single database server node. Instead of adding more machines, you upgrade the existing hardware to handle heavier workloads using commands like as-vm resize. This approach is straightforward because it requires no changes to your application logic or data distribution. You simply allocate more power to the same instance, allowing it to process requests faster and store more data within a single machine, though exceeding instance limits will cause immediate provisioning failures. Here is a practical configuration for vertical scaling using Azure Database for Postgres. We start with a standard B2MS instance that has limited vCPUs and RAM. To scale vertically, we update the performance tier to General Purpose, Gen 5.4. This single change provisions 4 vCPUs and 32 GB of memory. The script retains our storage settings and backup policies, ensuring the upgrade is seamless without losing data or changing connection strings, though misconfiguring the tier will trigger unexpected billing spikes. Vertical scaling has hard limits. You are constrained by the maximum size of a single server hardware offering like the standard GRS16 instance. Once you hit that ceiling, you cannot scale further vertically. Additionally, vertical scaling does not improve availability in the same way horizontal methods do. If the single node fails, the entire database goes down unless you have a separate high-availability failover mechanism. This is why vertical scaling is often the first step, but rarely the final solution for massive applications. Horizontal scaling, or scaling out, distributes the workload across multiple servers. In relational databases, this is commonly achieved through red replicas managed by as-SQL Replica Create. We maintain one primary node for all write operations like inserts and updates. Multiple replica nodes then handle read operations. This separation allows you to scale reads independently by adding more replicas as traffic grows, effectively multiplying your throughput without overloading a single machine, though network latency between regions can degrade query performance. Let's compare these two approaches side by side. Vertical scaling offers low complexity and quick implementation, but it comes with high hardware costs that rise exponentially as you move to D4DS v5 instances. Horizontal scaling is more complex to architect and manage, yet it provides virtually unlimited scale using commodity hardware. While vertical scaling has a single point of failure risk, horizontal scaling offers high availability through distribution. Understanding these trade-offs is key for the exam and prevents costly architectural missteps during production deployments. Now let's walk through a practical sequence for implementing your scaling strategy. First, you must optimize existing resources before spending money on new hardware. This involves checking for missing indexes and inefficient queries using the Query Performance Insight tool. Only after you have squeezed every drop of performance from your current setup should you consider upgrading. This prevents over-engineering and ensures you are solving the right problem before triggering unnecessary infrastructure costs during critical exam scenarios. Here is an example of optimizing resources through indexing. We create a non-clustered index on the customer email column using the createIndex command to speed up lookup queries. This reduces the database overhead by avoiding full table scans across millions of rows. The script also includes a comment explaining that this optimization targets read-heavy workloads, which is a common pattern in e-commerce applications where user profiles are frequently accessed, though missing statistics updates will cause query plan regressions. Next, once optimization is complete, you scale vertically to handle increased load on a single node. This is the path of least resistance. You upgrade the instance class using AZ-SQL DB update to get more vCPUs and RAM. This step buys you time and allows your application to grow without immediate architectural changes. It is cost-effective for moderate growth phases where horizontal complexity is not yet justified, though forgetting to schedule maintenance windows will trigger unexpected downtime during production deployments. Here is the configuration for scaling vertically. We update the instance class to a larger size using a JSON template, increasing vCPUs and memory. The script preserves our storage type and retention policies to maintain data integrity during the upgrade. This approach requires no application code changes, allowing you to deploy the new capacity quickly while monitoring performance metrics, though misaligned resource groups will cause deployment failures and leave orphaned resources in your subscription. Finally, when vertical scaling hits its hardware limits, you distribute the load horizontally. You add red replicas to handle read-heavy traffic and consider sharding for write-intensive workloads across multiple regions. This step introduces complexity, but provides virtually unlimited scale. You must ensure your application logic can handle eventual consistency and route reads to the appropriate replicas using connection strings, though ignoring replication lag will cause stale data reads and break critical transactional workflows. Here is application logic for routing reads to replicas. The code checks the query type and routes select operations to a randomly chosen replica from the pool using Azure Traffic Manager. Write operations are directed to the primary node. This pattern ensures that read traffic does not overwhelm the primary database, allowing you to scale reads independently while maintaining data consistency on writes, though misconfigured failover endpoints will cause connection timeouts during active development cycles. Let's check your understanding. You have a read-heavy news application that is experiencing latency during peak traffic. The primary database CPU usage is low, but read queries are slow. Which scaling strategy should you implement first? A. Vertical scaling to increase CPU. B. Sharding for write distribution. C. Read replicas to offload reads. Or D. Optimizing indexes only. Choosing the wrong path will waste budget and delay your certification exam score by ignoring the actual bottleneck. We covered the core concepts of database scaling. Vertical scaling upgrades a single node's power, offering simplicity but facing hard hardware limits like the D-series instance cap. Horizontal scaling distributes load across multiple nodes, providing massive scale at the cost of complexity. You should always optimize first, then scale vertically, and finally distribute horizontally when needed. Remember to handle eventual consistency and monitor your metrics closely using application insights to prevent silent data corruption. For the AZ-305 exam, focus on identifying the right scaling strategy based on workload characteristics. Vertical scaling is often the correct answer for moderate growth or when application changes are not feasible. Horizontal scaling is preferred for massive scale and high availability requirements. Pay attention to keywords like read-heavy, write bottleneck, and eventual consistency. Always consider optimization before recommending expensive hardware upgrades, as misreading these prompts will cost you critical points on your final certification test. Imagine driving on a single-lane highway during rush hour. Every car wants to go the same way, traffic grinds to a halt, and anyone trying to turn left gets stuck behind everyone else. That is exactly what happens when your application relies on one primary database for everything. As traffic grows, you will hit resource contention and geographic latency. Today, we will solve this by learning how to distribute read workloads and replicate data across the globe using Azure SQL Database geo-replication. We are going to cover 4 main areas today. First, we will look at how red replicas offload heavy query traffic from your primary instance. Second, we will examine the mechanics of asynchronous replication and its inherent lag. Third, we will explore global distribution strategies for reducing user latency. Finally, we will discuss consistency models and failover planning to keep your system resilient. You will learn to configure secondary servers in East US and West Europe, calculate cross-region bandwidth costs, and avoid catastrophic data loss during unplanned outages by mastering these exact architectural patterns. Before we dive into the architecture, let us define our core term clearly. A read replica is a secondary database instance that maintains an exact copy of your primary data, but operates in a strictly read-only mode. This means you can safely execute select queries against it without ever risking accidental modifications or deletions to your source of truth. For example, running complex reporting dashboards against this secondary endpoint prevents transaction log bloat on the master. Ignoring this boundary will cause immediate constraint violations and crash your production pipeline. In most modern applications, your database is heavily skewed toward reading data rather than writing it. Studies show that typical workloads perform roughly 70% reads and only 30% writes. By routing those heavy select operations to secondary instances, you preserve the primary database compute and storage resources for critical transactional updates. This separation prevents read-heavy traffic from choking your write pipeline. If you misroute write commands to a replica, the system will reject them with a read-only error code, halting your checkout process entirely. Let us look at how you actually implement this routing logic inside your application layer. The code snippet shows a simple connection factory that inspects the incoming query type. If the operation is a write, it connects directly to the master instance. Otherwise, it randomly selects a replica from your pool to distribute the load evenly across all secondary nodes. You must implement retry logic with exponential backoff for transient network timeouts. Failing to handle these drops will cause cascading failures during region failover events. Now let us move to the broader architecture of distributing your data globally. We will walk through this setup in 3 clear phases. First, we provision the primary database and enable the built-in replication feature within your Cloud Console. This establishes the baseline link between regions. You will use the AZ-SQL DB replica create command to spin up a secondary server in Japan East. Skipping network security group rules here will block cross-region bandwidth and prevent initial synchronization from completing successfully. Here is the exact command you would run to activate geo-replication for a managed database. The first block creates the primary instance in your target region with standard tiering. The second block immediately links a secondary replica in a different geographic zone, automatically configuring the network endpoints and encryption keys for secure cross-region traffic. You must verify that both servers share the exact same storage account configuration. Mismatched SKU tiers will trigger immediate replication failure and leave your disaster recovery plan completely untested. Second, you configure the failover policies and monitor the replication lag metrics. You will set the secondary region to automatically accept traffic if the primary goes offline, while continuously tracking how many seconds behind the master the replica falls. This ensures your disaster recovery plan matches your business continuity requirements. If lag exceeds 60 seconds during a regional outage, your application will serve stale inventory counts and trigger duplicate order processing for frustrated customers. Visualizing the data flow helps clarify how traffic actually moves through this topology. A global load balancer sits at the edge and routes incoming user requests to the nearest available region. Inside each region, a local read replica handles the select queries, while forwarding write operations back to the primary node for transactional integrity. You must configure health probes with a 3-second timeout interval. Misconfigured probes will route live traffic to degraded endpoints and cause widespread service degradation across your entire fleet. Finally, you implement read-your-writes consistency logic for critical user actions. When a customer performs a transaction, your application forces the subsequent read request to bypass the replica and query the primary instance directly. This guarantees immediate visibility of their own changes despite asynchronous replication delays. You should cache this primary endpoint temporarily using a short-lived token. Forgetting this bypass mechanism will cause payment confirmation screens to display zero balance and trigger unnecessary support tickets. When designing your global architecture, you must choose between 2 distinct replication models. Active-passive setups are simpler because only one region accepts writes, making failover straightforward but leaving the secondary idle. Active-active configurations allow writes anywhere, drastically improving availability but introducing complex conflict resolution when concurrent updates collide across regions. You will calculate a 15% cost premium for active-active cross-region bandwidth. Ignoring this pricing model will blow through your monthly cloud budget and trigger service suspension notices. Let us pause and test your grasp of replication lag. Consider a scenario where a user updates their profile on the primary database, then immediately refreshes their dashboard on a red replica. What will they see, and how should you architect around this behavior? Think about the timing of asynchronous data propagation. You must implement a local cache or force direct reads for the first 5 seconds after any write operation. Failing to address this window will display outdated user preferences and break personalized recommendations entirely. Remember this fundamental trade-off when designing distributed systems. You must always decide whether your application can tolerate slightly stale data in exchange for faster response times, or if it requires immediate accuracy at the cost of higher latency. Choosing the right consistency model dictates your entire infrastructure architecture. For financial ledgers, you enforce strong consistency with synchronous replication across availability zones. Selecting eventual consistency for those same records will cause reconciliation failures and trigger immediate audit compliance violations. Let us quickly review the core takeaways from today's session. Read replicas effectively scale read-heavy workloads by offloading select queries from the primary instance. Asynchronous replication introduces minor lag, so you must implement consistency logic for critical transactions. Geo-replication reduces geographic latency and serves as your foundation for disaster recovery planning. You will apply these patterns to Azure SQL Database Elastic Pools and monitor query performance using the DMDB resource stats dynamic view. Skipping this monitoring step leaves you blind to resource throttling events. For the certification exam, focus heavily on recognizing when to use read replicas versus active-active topologies based on workload characteristics. You will likely encounter scenario questions about resolving replication lag or calculating cross-region data transfer costs. Memorize the trade-offs between consistency and availability, and always prioritize optimizing queries before scaling infrastructure. The test will specifically ask you to select the correct failover priority level for a Tier 3 business application. Choosing the wrong priority will cause automatic failover delays exceeding your SLI requirements. Imagine a library where anyone can walk in, take any book home, and scribble in the pages without consequence. That is exactly what your database looks like without a solid security strategy. Today, we will design the proper access controls, configure Azure SQL Database auditing, and implement strict log retention policies. Without these measures, you risk catastrophic data breaches and fail every compliance audit. Let us build those essential locks, guards, and logbooks together right now. We will cover the core pillars of database security, implement least privilege using Azure, our back and specific IAM roles, explore detailed auditing strategies including system-defined triggers, and review best practices to avoid common architectural pitfalls. If you skip these steps, your environment becomes vulnerable to unauthorized data exfiltration and fails strict regulatory checks. We will also walk through practical CLI commands to harden your infrastructure securely today. Security rests on 4 critical pillars that every architect must master. First, identity and access management verifies connections using multi-factor authentication and managed identities. Second, encryption at rest protects physical storage from disk theft using IES-256 algorithms. Third, encryption in transit secures data moving over the network via TLS 1.2 protocols. Finally, dynamic data masking hides sensitive fields from non-privileged users while keeping underlying records intact for operational workflows. This SQL block enforces least privilege by creating a specific reporting role for business intelligence services. We grant only select access on relevant tables, then create a dedicated service principal and assign them to that role instead of using a generic admin account. If you skip this step, developers accidentally gain write permissions, leading to accidental schema drops or malicious data manipulation during production deployments. First, we enforce least privilege by creating specific database roles and actively revoking public access to ensure every user only sees exactly what they need. We will run the alter role command to explicitly deny wildcard permissions across all schemas. Failing to restrict default grants creates a massive attack surface where compromised credentials can immediately dump entire production tables into an attacker environment. Here we apply dynamic data masking to protect sensitive columns across your production environment. We alter the user's table to mask email addresses using a default function and phone numbers with a partial reveal, so support staff can verify records without seeing raw private details. If you misconfigure these rules, customer service representatives might accidentally expose full social security numbers during routine troubleshooting calls. Next, we mask sensitive columns using dynamic data masking functions within the database engine. We will configure the default and partial reveal types to ensure non-privileged users can verify records exist without exposing the underlying private data. Skipping this configuration leaves personally identifiable information completely visible to application layers that should only require minimal access for operational tasks. An audit trail is the immutable record of all database activities within your infrastructure. It captures exactly who changed a record, when they changed it, and what the previous value was, providing a forensic trail for compliance and security investigations. If you disable these logs, you will fail SOC 2 requirements and lose the ability to trace ransomware propagation back to its initial entry point. Finally, we implement auditing triggers to capture every update operation across critical tables. This pattern logs old and new values into a separate audit table using the insert statement syntax, ensuring accountability for high-risk changes. If you neglect this step, financial discrepancies will remain hidden until auditors discover missing transaction records during quarterly compliance reviews. This trigger captures changes to the user's table using the after update clause. When an update occurs, the function logs the action type, the user who made the change, and both the old and new values into the audit log table, preserving a complete history. If you forget to add error handling, failed transactions will still generate false audit entries that clutter your monitoring dashboards. This flow shows how an audit trigger processes a request inside the engine. The application sends a query, the database engine evaluates the trigger, and if it is an update, the data is written to both the main table and the audit log for later forensic analysis. If you route logs to unencrypted storage, attackers can easily delete those records before investigators can reconstruct the breach timeline. Compare these practices against common pitfalls using the provided matrix. Always automate secret rotation with Azure Key Vault and deploy databases inside private subnets, while strictly avoiding hard-coded credentials, overlogging which degrades query performance, and neglecting immutable backups with soft delete enabled. Missing these controls will cause critical service outages during credential expiration events. Encryption protects the data at rest, but auditing proves exactly who touched it during runtime. You need both mechanisms to satisfy strict compliance frameworks like HIPAA and investigate incidents effectively. If you only enable one, you will either face regulatory fines for unencrypted storage or fail to identify the compromised service principal responsible for the breach. Which SQL Server feature tracks server-level and database-level events natively without custom code. Think about native auditing tools like the built-in SQL audit capability. You must understand this distinction because relying on manual logging scripts creates massive maintenance overhead and frequently misses critical privilege escalation attempts during peak production traffic, leaving your compliance reports dangerously incomplete and unactionable. We covered the core pillars of security, implemented least privilege with specific roles, masked sensitive data using dynamic functions, and designed an auditing strategy using system triggers. Remember to automate secrets rotation and audit selectively to prevent storage bloat. Failing to implement these controls will cause unnecessary egress charges and leave your infrastructure exposed to unauthorized administrative access. For the AZ-305 exam, focus heavily on least privilege implementation using Azure, are back and specific encryption types. You must know when to use native auditing versus application-level audit tables for compliance scenarios. Remember that manual security processes are prone to human error, so always prefer automated key rotation and integrated monitoring dashboards during your certification test. Imagine you are shipping a valuable package across the country. You can either lock the outer box so no one opens it without the key, or write the contents in invisible ink only the recipient reads. In Azure SQL Database, we face this exact choice between transparent data encryption and always encrypted. TDE secures physical, MDF files at rest, while IE protects specific columns inside the engine. Choosing incorrectly leaves PII exposed to cloud admins or violates compliance audits. Let us proceed. We will start by examining transparent data encryption fundamentals and how it secures files at the storage layer using IES-256. Next, we dive into always encrypted architecture and its client-side driver workflow with Azure Key Vault integration. Then we walk through designing your encryption strategy step by step. Finally, we cover AZ-305 exam tips to prevent costly configuration mistakes during the certification assessment. Transparent data encryption actively encrypts database files at the storage layer to protect data at rest from physical disk theft. It operates completely transparently to your application, requiring zero code modifications or connection string updates. The primary goal is securing underlying MDF and LDF files against unauthorized access if storage media is compromised or lost during migration. TDE performs I/O encryption and decryption of the database, backups, and log files automatically. When data is written to disk, it encrypts instantly. When read, it decrypts seamlessly. This file-level operation remains completely transparent to your application logic. Remember that over 90% of regulatory frameworks require encryption at rest, making TDE a mandatory baseline for meeting SOC 2 and HIPAA audit requirements in enterprise environments. Here is how you configure TDE in SQL Server using TransactSQL commands. First, create a master key in the master database with a strong passphrase. Next, generate a server certificate protected by that master key. Then, inside your target database, create a database encryption key using IES-256 and encrypt it with the server certificate. Finally, execute alter database, set encryption ON to activate the process immediately. Now let us look at how always encrypted handles data flow through your architecture. The process begins with the client application sending a query. The driver intercepts this and encrypts sensitive columns using the column encryption key before sending the request to SQL Server. The server stores only ciphertext. When reading, the server returns encrypted data, and the driver decrypts it locally using the master key stored securely in Azure Key Vault Managed HSM to prevent insider access. Always encrypted is a feature that ensures sensitive data remains encrypted within the database engine itself. It uses a strict two-tier key architecture featuring a column encryption key for the actual data and a column master key to protect that encryption key. The database engine never processes plain text, ensuring that even privileged administrators cannot access the raw information during routine maintenance or backups. Always encrypted provides granular control by allowing you to encrypt specific columns rather than the entire database. It supports randomized encryption for maximum security or deterministic encryption when you need equality searches and exact matching. However, this comes with strict trade-offs. You cannot perform range queries or pattern matching on encrypted columns, and there is a noticeable performance overhead due to cryptographic operations at the application tier. Let us move to the core procedure for your architecture design work. We will walk through designing your encryption strategy step by step using a structured methodology. This process ensures you select the right controls for your specific threat model and compliance needs, while preventing misconfigured keys that could lock out legitimate users during production deployments. In the first step, you must identify data sensitivity across your schema. Classify your columns based on regulatory requirements and business impact using a formal risk matrix. For example, mark social security numbers and credit card details as highly sensitive PII requiring IE. General metadata like usernames may only require standard protection. This classification drives your encryption scope and prevents overengineering. With your data classified, we proceed to the second step of the workflow. You will select the encryption layer based on the sensitivity levels you identified earlier. This decision balances strict security requirements against application complexity and performance constraints, while ensuring your chosen controls align with AZ-305 scenario expectations and audit standards. For the second step, select your encryption layer based on specific workload requirements. Use transparent data encryption for compliance requirements that mandate encryption at rest across all files. Use Always Encrypted for highly sensitive columns where you cannot trust database administrators or cloud operators. This hybrid approach provides defense in depth while managing performance impact effectively during peak traffic. Use this comparison table to finalize your design decisions before deployment. TDE protects the entire database with minimal application changes and low complexity using IES-256. Always Encrypted secures specific columns, but requires driver configuration and offers higher performance overhead. Consider both features together for a robust security posture that satisfies strict compliance audits without breaking existing queries. Remember this principle as you design your cloud solutions. Security is layered, and relying on a single control is rarely sufficient for production workloads. Always ensure your key rotation policy is automated through Azure Key Vault to prevent catastrophic data loss from expired or misplaced keys during scheduled maintenance windows. Let us test your understanding with a practical scenario. Which encryption technology should you choose if you need to protect data from physical theft while requiring zero application code changes? Think about the scope and transparency of each option before checking the answer, as confusing these features will cost you points on the certification exam. We have covered the essential concepts for this module. TDE secures files at rest and meets compliance baselines using IES-256 storage encryption. Always Encrypted protects sensitive columns from administrators using client-side keys stored in Azure Key Vault. Designing your strategy requires identifying sensitivity, selecting the right layer, and managing keys securely to avoid lockouts. For the exam, focus heavily on distinguishing between TDE and Always Encrypted use cases. You will likely encounter scenarios asking you to choose between them based on specific threat models. Remember that TDE protects against physical theft, while IE mitigates insider threats. Also, expect questions about key management best practices and query limitations with encrypted columns to test your practical knowledge. Imagine a library where every book is stored in the basement. To read one page, you have to walk down, find the shelf, and climb back up. That is your application waiting on a database. Azure Cache for Redis moves those books to a desk right in front of you, turning slow trips into instant reads. If you skip this layer, SQL Server will choke under concurrent load, causing timeouts. We use the AZ-Redis create command with a 256 megabytes size to provision it quickly, ensuring IPI responses drop from 2 seconds down to 50 milliseconds. We will start by defining the cache-aside pattern, the standard way to wire Redis into your apps. Then we will walk through a C# implementation example using Stack Exchange, Redis to see the code in action. Next, we will use a Blackboard approach to implement a production-grade pattern covering connections, TTLs, and resilience. After that, we will compare key scenarios like session state and rate limiting. Finally, we will review exam hints and common pitfalls. Missing this flow causes connection pooling errors and memory leaks that crash your worker roles during peak traffic. The most common architectural pattern for integrating Redis with a relational database is the cache-aside pattern. Also known as lazy loading, this approach means the cache does not automatically update when the database changes. Instead, the application acts as the gatekeeper, checking the cache first and only querying the database when necessary. If you skip this check, you bypass performance gains entirely, causing unnecessary write locks on your SQL server and triggering deadlocks under heavy concurrent loads. Here is how we implement cache-aside in C# using the Stack Exchange, Redis library. First, we construct a cache key based on the product ID using string interpolation. We then attempt to retrieve it from Redis asynchronously via the string_getAsync method. If the value exists, we deserialize and return it immediately. If it is a miss, we query the database, serialize the result, and store it back in Redis with a 30-minute expiration time. Forgetting this step triggers thundering herd errors that crash your backend during flash sales. To implement a production-grade Redis pattern, we must follow 3 critical steps. First, we establish a singleton connection to avoid overhead. Second, we apply expiration policies to manage memory and staleness. Finally, we design failure resilience so the app survives if the cache goes down. Skipping these steps causes socket exhaustion on your Azure App Service, leading to unhandled exceptions that bring your entire microservice cluster offline during routine deployments. For the first step, we configure the connection multiplexer as a singleton. In this code, we use the static factory method to create one shared instance. We then inject this multiplexer into our service via dependency injection using add-singleton. This ensures that all requests share the same underlying TCP connections, drastically reducing network overhead. Failing to do so creates thousands of ephemeral ports per second, exhausting your Linux VM capacity and forcing Azure Load Balancer to drop active sessions. Now we add the second step to our board, applying expiration policies. In production, we never store data indefinitely without a TTL. This prevents memory bloat and ensures that stale data is eventually evicted, keeping our cache fresh. Without explicit time-to-live values, your Azure cache for Redis will hit the 250 megabyte standard tier limit quickly, triggering eviction warnings that force the system to drop critical session tokens unexpectedly. Here is how we apply expiration policies in code. When setting a value, we pass a time span to define the time to live. In this example, we set a 30-minute window using the string_setAsync method. This ensures that if the database changes, the cache will eventually reflect the truth without manual invalidation logic. Ignoring this rule leaves outdated pricing data visible for hours, causing customer complaints and triggering failed payment gateways during checkout flows. Finally, we add the third step, designing failure resilience. Redis is ephemeral. It can go down. We must wrap our cache logic in try-catch blocks so that if the cache fails, the application falls back to the database gracefully without crashing. Forgetting this safety net causes unhandled exceptions that bubble up to your Azure Monitor alerts, forcing automated scaling events that waste compute resources and delay customer requests by several seconds. Here is the resilience pattern in action. We wrap the cache operations in a try-catch block. If a Redis command exception occurs, we catch it and proceed directly to the database query using direct SQL execution. This ensures that a cache outage does not take down your entire application. Skipping this fallback path causes 503 service unavailable errors across all IPI endpoints, completely blocking user authentication and payment processing during network partitions. Let's compare the key scenarios where Azure Cache for Redis shines. For database query caching, use it for complex joins that rarely change. For session state management, move data out of server memory to enable horizontal scaling across multiple virtual machines. And for rate limiting, use atomic operations like increment to track request counts securely. Misconfiguring these patterns causes race conditions that corrupt user shopping carts and trigger false positive fraud alerts during peak holiday traffic. Let's check your understanding. You have a high-traffic IPI and a popular product key expires. Suddenly, hundreds of requests hit the database simultaneously to repopulate the cache. What is this phenomenon called, and what is the solution? This thundering herd problem overwhelms your SQL server, causing query timeouts and memory pressure. The fix involves implementing distributed locks or staggered expiration windows using Redis keys with randomized TTL offsets to smooth out the load spikes. To recap, Azure Cache for Redis reduces latency by moving data to RAM. Use the cache-aside pattern to load data on demand. Implement production patterns by using singletons, setting TTLs, and handling failures gracefully. And always remember, treat the database as the source of truth. Ignoring these principles causes cached stale records to persist indefinitely, leading to incorrect financial calculations and violating compliance audit requirements for data accuracy. For the AZ-305 exam, focus on these points. You must know how to configure SSL and Microsoft Entra ID for security. Understand the difference between basic, standard, and premium tiers, especially regarding persistence and clustering capabilities. And remember that Redis is not a replacement for your primary database. It is an acceleration layer. Confusing these roles causes architects to deploy cache-only solutions that lose all transactional data during planned maintenance windows. Imagine a city's power grid versus every house having its own massive generator. If everyone runs their air conditioning at once, the grid handles the surge by sharing load from other neighborhoods that are currently idle. Azure SQL Elastic Pools work exactly like that shared grid for your databases, allowing you to manage performance and cost across a group of databases rather than provisioning each one individually. In this lesson, we will explore how Elastic Pools share CPU and memory across multiple databases using vCore pricing models. We will walk through the exact Azure CLI commands to provision a Gen 5 pool with 2 dedicated cores. Then we will cover best practices for right sizing and monitoring metrics. Finally, we will review common exam pitfalls regarding service tier mixing and storage caps that frequently appear on the AZ-305 certification. An Azure SQL Elastic Pool is a collection of multiple databases that share a single set of compute and storage resources. Instead of assigning a fixed performance level to each database, you assign a total budget measured in vCores or EDTUs to the pool. The databases consume these resources dynamically based on their current workload, which allows for bursting when traffic spikes and reduces costs during idle periods, though misconfigured limits can cause unexpected throttling. Elastic pools use EDTUs or vCores as the unit of measure for compute capacity. You can set a minimum guarantee for each database to ensure noisy neighbors do not starve others. You can also set a maximum cap to prevent a single runaway process from consuming the entire pool capacity. This design is ideal for multi-tenant applications where usage patterns are variable and staggered, but failing to cap max EDTUs will leave you vulnerable to sudden budget overruns. To design an effective elastic pool, we follow a sequential process starting with workload analysis. First, we analyze historical usage patterns using performance counters to determine the aggregate load across all tenants. This ensures we provision enough resources without overpaying for unused capacity. Skipping this step often leads to severe underprovisioning during peak hours or unnecessary spend during off-peak maintenance windows. We start by creating the resource group and SQL Server using standard Azure CLI commands. Then, we create the Elastic Pool itself with a single command specifying Gen 5 hardware and 2 vCores with 100 gigabytes of storage. This command establishes the shared budget that all databases in this pool will draw from, though forgetting to assign a region early can cause deployment failures across linked services. Next, we configure the pool limits and add databases using targeted PowerShell or CLI scripts. We must ensure that each database has min and max capacity settings to prevent any single tenant from monopolizing the shared resources. Properly capping these values protects against runaway queries, while neglecting them will inevitably trigger performance degradation across your entire multi-tenant environment during concurrent peak loads. Once the pool exists, we create a new database directly inside it using the Elastic Pool name parameter. We use the exact flag to link the database to our shared budget in the command line. This command places tenant database 0, 1 into MyElasticPool, allowing it to burst up to the pool total vCore limit, though misnaming the pool will cause immediate provisioning errors and block tenant access. Finally, we set resource limits and monitor for exhaustion using Azure Monitor dashboards. We define min capacity to guarantee performance and max capacity to cap usage across all linked databases. Monitoring CPU percentage helps us detect throttling early and scale proactively, but ignoring alert thresholds will leave you blind to sudden compute saturation until customer complaints actually arrive. We can update an existing database to set its min and max capacity within the pool using the AZ-SQL DB update command. The min value ensures a performance floor so the database is not starved during heavy pool usage. The max value prevents a single database from consuming all vCores, protecting other tenants from unexpected budget spikes and service degradation. When deciding between a standalone database and an elastic pool, consider your workload characteristics carefully. Standalone databases offer fixed performance, but can be costly for variable workloads that fluctuate daily. Elastic pools provide cost efficiency and simplified management by sharing resources across a group of databases, though choosing the wrong model will either waste budget or cause severe latency during traffic surges. To maintain stability, always right-size your pool based on the 95th percentile of historical aggregate usage metrics. Monitor for pool exhaustion using Azure Monitor alerts on CPU percentage and DTU consumption rates. Be aware of the noisy neighbor effect. Without proper limits, one poorly optimized query can degrade performance for all other databases in the pool, triggering cascading timeouts across your application. Let's check your understanding with a practical scenario. You have a SaaS application with 50 tenant databases that remain mostly idle at night, but spike heavily during business hours. Which design approach saves the most cost while handling traffic spikes? Is it provisioning 50 standalone databases or using an elastic pool configured with appropriate vCore limits and monitoring alerts? We have covered the core concepts of Azure SQL Elastic Pools and their operational benefits. These pools provide cost efficiency by sharing resources across databases with fluctuating workloads. They allow bursting when necessary and simplify governance through centralized management using standard Azure CLI workflows. Always plan your pool size based on historical metrics to ensure stability and avoid unexpected compute throttling during peak demand. For the AZ-305 exam, focus on common pitfalls regarding service tier restrictions and storage caps. Remember that you cannot mix general purpose and business-critical tiers in the same pool. Ensure the sum of database storage does not exceed the pool total storage limit. Also, be aware of Azure SQL Elastic jobs for running scripts across multiple databases simultaneously without triggering manual orchestration errors. Imagine a factory assembly line where every car is built from scratch by hand versus using a single blueprint that tells the machine exactly which parts to assemble for each model. Azure Data Factory metadata-driven patterns work exactly like that blueprint, allowing you to process diverse data sources without rewriting code for every table. Mastering this approach prevents pipeline sprawl and keeps your certification exam ready, because hard-coding tables quickly breaks when business requirements shift overnight. We will cover 4 key areas for your upcoming certification exam. First, we define the metadata-driven architecture and how control tables replace hard-coded logic in Azure Data Factory. Second, we look at incremental load strategies using watermark columns to optimize data movement. Third, we examine hub-and-spoke orchestration for modular pipelines. Finally, we dive into parameterization techniques for dynamic execution. Skipping these patterns will cause deployment failures when your production environment scales beyond initial testing limits. The metadata-driven pattern is a design approach where pipeline logic is driven by data stored in a control table rather than hard-coded activities. This enables dynamic scaling and maintenance across Azure SQL Database or Cosmos DB. Instead of creating separate pipelines for each source, you store metadata like table names and schemas in a dedicated control database. Your pipeline reads this list at runtime to process everything automatically, which prevents configuration drift and stops orphan datasets from breaking your nightly refresh schedules. We define a copy data activity with explicit source and sync inputs for your exam scenarios. The dataset references point directly to our generic source dataset and sync dataset objects inside the Azure portal. Inside the type properties, we specify SQL source and sync types for the data transfer. This structure allows us to reuse the same copy logic across different tables by swapping parameters dynamically. Failing to parameterize these links will cause pipeline failures when you promote code through dev test prod environments without updating connection strings manually. First, we define the control table that holds our metadata using a dedicated Azure SQL Database instance. This table stores the list of tables or files to process along with their exact schemas and watermark columns. You must configure proper indexing on these columns to prevent query timeouts during large dataset scans. Skipping this step will cause your orchestration engine to stall, triggering hard failures when downstream systems expect timely data refreshes within strict SLI windows. The lookup table's activity connects directly to our ControlDB linked service using standard Azure SQL authentication. We set a 12-minute timeout for the query to handle complex schema queries safely. The pipeline property references a getTableList pipeline, passing in an environment parameter to filter the results dynamically. This lookup retrieves the metadata list that drives the rest of the pipeline. If you omit proper retry policies here, your orchestration will abort immediately when network latency spikes during peak production hours. Next, we add the lookup and for each activities to your orchestration canvas. The for each iterates through the metadata list retrieved by the lookup, processing each item sequentially or in parallel based on your concurrency settings. You should configure a maximum degree of parallelism, around 25, to avoid exhausting your Azure integration runtime capacity limits. Ignoring these throttling boundaries will trigger resource contention errors that silently degrade your overall data refresh performance. We create a for-each activity named for-each table inside your pipeline designer. It depends directly on the lookup table's activity finishing successfully before proceeding. The items property pulls the first row from the lookup output using standard JSON path syntax, passing each table record into the loop for processing. This ensures we handle every metadata entry in our control list. Failing to validate the JSON array structure will cause silent loop failures when your control database returns unexpected null values. Finally, we wire dynamic parameters directly into your pipeline configuration. Inside the for-each loop, we use dynamic expressions to map the current item's metadata to the copy activity parameters, ensuring each iteration processes the correct table. You must validate these references using the built-in expression tester before publishing to production. Incorrectly mapped variables will cause data truncation errors when mismatched schemas attempt to write incompatible column types into your destination warehouses. We configure the copy activity with a SQL source and sync directly in the Azure portal. The linked service points to our target database using managed identity authentication. We set a 30-minute timeout policy to handle large transfers without dropping connections. This setup allows the pipeline to dynamically use parameters from the for-each loop for each table. Neglecting to configure proper retry logic here will cause incomplete batch loads when network interruptions occur during peak synchronization windows. Incremental load strategies significantly reduce data transfer volume by up to 90%. Instead of copying entire datasets daily, you track a watermark value using standard data time columns. This approach processes only new or modified records, saving costs and improving performance. You must implement lookup activities for old and new watermarks, filter queries based on these values, and update the control table after each run. Failing to secure these watermark columns will cause duplicate record ingestion that corrupts your downstream analytics reports. Full loads copy all data every time, resulting in high data volume and significant storage cost impact. Incremental loads reduce volume by processing only changes, lowering costs, but adding moderate complexity to your orchestration logic. Full loads have simple implementation, but delayed latency for downstream consumers. Incremental loads offer near real-time freshness with slightly more setup effort. Misconfiguring your load frequency will trigger excessive compute billing spikes when Azure Data Factory repeatedly processes already synchronized datasets. Hub-and-spoke orchestration improves modularity by separating master logic from child tasks inside your Azure Data Factory workspace. A trigger event starts the master orchestrator, which then executes child pipelines using standard invoke methods. The master handles global variables and error logging, while children perform specific data movements. Finally, results are logged for observability. Neglecting proper dependency chains between these components will cause cascading failures that bypass your centralized monitoring dashboards during critical batch windows. Modularity turns complex pipelines into manageable, reusable components for your certification exams. By breaking logic into child pipelines, you simplify maintenance and enable parallel execution across different data domains. You should configure separate integration runtime groups to isolate high-volume workloads from lightweight transformations. Failing to compartmentalize these workflows will create resource bottlenecks that delay critical reporting deliverables when multiple departments request simultaneous data refreshes. Test your understanding before moving forward. In the metadata-driven pattern, what activity iterates through the list of tables retrieved from the control table? The answer is the for-each activity, which loops over the metadata items and executes child processes for each entry. You must validate this configuration using pipeline validation endpoints to catch syntax errors early. Skipping this verification step will cause silent runtime failures when your orchestration engine encounters malformed JSON arrays during production deployments. We covered 4 essential patterns for your upcoming certification exam preparation. Metadata-driven architectures scale pipelines automatically using control tables stored in dedicated databases. Incremental loads save cost and time by tracking watermarks across large datasets. Hub-and-spoke orchestration improves modularity through master-child relationships that isolate failure domains. Parameterization enables dynamic execution across diverse data sources. Neglecting these core concepts will result in rigid architectures that cannot adapt to shifting business requirements or scale beyond initial testing boundaries. Focus on Git integration for version control in Azure Data Factory during your exam preparation. Know SHIR scaling requirements for on-premises data movement across hybrid network boundaries. Use Key Vault for secrets and never hardcode credentials into linked services or pipeline parameters. Error handling paths are critical for exams, so always implement failure branches for logging. Skipping these security protocols will trigger immediate certification failures when reviewers evaluate your compliance with enterprise governance standards. Imagine a city's water supply system where every pipe leaks and filters are clogged without warning. Chaos ensues, right? In data engineering, we face the same risk when pipelines lack structure. Without a robust architecture using services like Azure Data Factory or Logic Apps, your data becomes unreliable, siloed, and impossible to trust for critical business decisions. Today, we'll design a resilient pipeline that keeps your data flowing cleanly from source to insight, ensuring high availability and auditability for your exams and real-world workloads. We'll start by comparing ETL and ELT architectures to pick the right pattern for your workload, focusing on when to use Azure Synapse versus Databricks. Next, we'll break down the anatomy of a modern pipeline into its core stages, identifying where latency risks hide. Then we'll dive deep into designing for resilience using idempotency patterns and change data capture with SQL Server CDC or Azure Database for MySQL. Finally, we'll cover best practices and common pitfalls to avoid on the exam, ensuring you can architect solutions that scale securely under pressure. Data integration relies on 2 primary patterns, ETL and ELT. In ETL, you extract data, transform it offline using Azure Databricks clusters, and load the clean result into a warehouse. This suits strict compliance needs where data must be masked before storage in Azure SQL Database. ELT flips this. You load raw data directly into a cloud warehouse like Synapse Analytics using the copy into command and transform it in place via T-SQL or Spark jobs. Modern cloud warehouses make ELT dominant due to decoupled storage and compute, reducing infrastructure management overhead significantly. Let's compare these patterns side by side to see where each fits best. ETL requires heavy preprocessing compute, but reduces load on the destination, ideal for low-bandwidth environments. ELT shifts transformation costs to the warehouse, enabling faster ingestion and schema-on-read flexibility. For latency, ETL often introduces delay due to pre-processing steps, while ELT offers near real-time availability once data lands. Choose ELT when you need subminute freshness for dashboards using Power BI, but stick to ETL if your source system cannot handle concurrent read loads during bulk transfers. A key term you must master is change data capture. CDC tracks row-level changes like inserts, updates, and deletes in source databases using capture instances or log-based tools. Instead of full table dumps that drain resources, CDC captures only the deltas. This drastically reduces network load and improves latency, making it essential for efficient data synchronization. Use Azure Database for MySQL with bin logs or SQL Server with SIS. FNCDC get all changes to stream updates efficiently, preventing timeout errors during large synchronization windows. Now let's design for resilience. A pipeline must survive failures without corrupting data. We'll build this through 3 steps. First, we ensure idempotency so retries never create duplicates. This means your logic handles repeated executions safely, critical when Azure Data Factory triggers fail and restart automatically. Without idempotency, a network blip could double-count revenue metrics, skewing financial reports and violating audit requirements for accurate historical records across your data lake layers. Here is an idempotent load function. It checks for existing records by primary key before inserting. If data exists, it updates the record. Otherwise, it appends new rows using a merge statement in T-SQL. This logic ensures that running the pipeline multiple times yields the same result, preventing duplicate entries during retries. For example, use merge into sales target using source ON. When matched, then update, guaranteeing data consistency even if Azure functions crash midway and retry with partial batches. Next, we add CDC to minimize resource waste. By tracking only changed rows, we avoid full dumps and improve latency. This approach is vital when processing terabytes of daily events. If you rely on full scans, query timeouts will occur, causing pipeline failures in Azure Synapse. Using CDC ensures you only move relevant deltas, keeping costs predictable within your budget caps and maintaining SLI compliance for downstream analytics workloads that depend on fresh data streams. This code extracts only delta records modified since the last sync timestamp. It queries the source for rows newer than a watermark and returns them as a data frame. After processing, we update the watermark to mark completion, ensuring we never reprocess the same data twice. Use the @pipeline, parameters, last sync time, parameter in Azure Data Factory to pass watermarks dynamically, preventing stale data ingestion and avoiding duplicate processing errors that corrupt your incremental load history. Finally, we use declarative orchestration to manage transformations. Tools including dbt allow you to version control logic and keep documentation alongside code, making pipelines maintainable and auditable. This is crucial for exam scenarios requiring governance. Declarative models ensure that transformation steps execute in the correct dependency order automatically. Without this structure, manual scripts can fail silently or run out of sequence, leading to missing rows in reports and requiring tedious manual reconciliation by your data engineering team. This dbt model defines a materialized table view using the materialized table config. It groups sales by customer, filters for completed orders, and aggregates revenue with sum, amount. The declarative config ensures that the transformation logic is version controlled and automatically documented via dbt docs generate, reducing maintenance overhead. Run dbt run m sales summary to execute only this model incrementally, saving compute credits in Snowflake and ensuring rapid iteration while maintaining data quality checks across your warehouse layers. Remember the fail-fast principle. Configure your orchestration to alert immediately upon failure. The longer an error goes undetected, the harder it is to reconcile downstream data and recover lost metrics. Set up Azure Monitor alerts with a 5-minute threshold for pipeline failures. This ensures you catch issues like bad schema changes before they propagate. Delaying detection can cause cascading errors across dependent jobs. resulting in significant data gaps that require expensive manual remediation and violate your service level objectives. Quick check: why is idempotency critical for pipeline reliability? A. It speeds up data ingestion. B. It prevents duplicate records on retries. C. It encrypts sensitive data. D. It reduces storage costs. Consider a scenario where Azure Data Factory retries a failed copy activity. If your load logic lacks idempotent checks, you risk inserting the same batch twice, corrupting your fact tables and inflating KPI metrics. Select the option that guarantees consistent results, regardless of execution count. We covered ETL versus ELT patterns, choosing ELT for cloud scalability using services including Synapse or Databricks. We designed resilient pipelines using idempotency to handle retries safely with merge statements, CDC to capture deltas efficiently via bin logs, and declarative orchestration for maintainability with dbt. Always prioritize data quality and modular design. These strategies ensure your architecture meets compliance standards, handles scale gracefully, and passes exam questions focused on optimizing cost, latency, and reliability in modern data ecosystems. For the AZ-305 exam, focus on selecting the right pattern for compliance versus agility. Know how CDC reduces load compared to full dumps by tracking only changes. Expect questions on idempotency benefits and declarative tools, including dbt for governance. Always choose modular, automated solutions over monolithic scripts. Review Azure Data Factory, trigger configurations, and Synapse pipeline error handling. Mastering these details ensures you can architect secure, scalable solutions that align with Microsoft's best practices for data platform engineering and cloud architecture certification. Imagine a massive library where books are stored in the basement, cataloged on the second floor, and analyzed by researchers in the attic. Moving those physical volumes between floors creates bottlenecks and delays. Azure Synapse Analytics solves this architectural problem by unifying storage and compute into a single cohesive workspace. You can now ingest terabytes of raw sensor data directly into Azure Data Lake Gen2 and run distributed queries without copying files. This consolidation matters because fragmented pipelines cause costly egress fees and stale reports, while a unified workspace keeps your data fresh and compliant. We will explore the core components of Synapse Analytics design by diving into dedicated SQL pools versus serverless options, understanding Spark integration for massive datasets, and applying performance tuning strategies to optimize cost and speed. You will configure a DW100C pool for predictable reporting workloads while pairing it with serverless endpoints for ad hoc exploration. Mastering these distinctions prevents runaway compute bills and ensures your data platforms scale reliably under heavy enterprise query loads during peak business hours. The Synapse Workspace serves as the central management plane and unified environment for all your analytics activities across enterprise data platforms. It acts as the container that holds your SQL pools, Spark pools, and integration runtime configurations within a single resource group. You will assign specific RBAC roles like contributor or reader to control access for data engineers and scientists. Proper workspace scoping prevents permission sprawl and ensures audit logs remain centralized for compliance reviews across regulated industries. When designing your solution, you must decide between dedicated SQL pools and serverless SQL pools based on workload predictability and budget constraints. This table compares their key characteristics to help you make the right choice for your specific data pipeline requirements. You will evaluate compute scaling limits against pay per query metrics to align infrastructure spending with actual usage patterns. Choosing incorrectly often leads to either wasted reserved capacity or unexpected throttling during critical monthly reporting cycles. We will walk through the design principles for building a high-performance Synapse solution by starting with SQL pools, moving to serverless querying, and finally covering Spark integration. You will apply distribution strategies like hash or round robin to optimize join performance across massive fact tables. Proper index selection directly impacts query execution time and storage consumption. Skipping these foundational steps typically results in slow dashboard loads and inflated monthly compute charges that drain project budgets quickly. For dedicated SQL pools, performance hinges on distribution and indexing strategies that directly control query speed. Here is a CTIE's pattern for efficient data loading using the create table as select command. First, we create a staging table with round-robin distribution for fast ingestion. Then, we use CTIEs to transform the data into a final fact table with hash distribution for joins and a column store index for analytical queries. Finally, we perform an atomic table swap to ensure zero downtime during production deployments. We now expand our design considerations to include serverless SQL pools that allow you to query data directly from your data lake without managing infrastructure. You will configure external tables pointing to AZ-305 Gen2 paths and leverage automatic file format detection to accelerate ingestion workflows. This architecture eliminates server provisioning overhead while maintaining strict security boundaries. Misconfigured path references frequently cause permission-denied errors that halt automated ETL jobs and delay critical downstream analytics pipelines. For serverless SQL pools, you query data directly from AZ-305 Gen2 using the OpenROWSET function to read Parquet files efficiently. We use a wildcard path for partition elimination and specify the Parquet format to enable predicate pushdown. The engine scans only the relevant columns and partitions to minimize cost and latency. This approach drastically reduces compute consumption during exploratory analysis, though poorly optimized predicates can still trigger full table scans that waste allocated credits unexpectedly. We finally add Spark pools to our design principles as a distributed engine for big data processing, machine learning, and real-time streaming. You will configure cluster scaling parameters like node count and driver memory to handle massive CSV ingestion workloads. This complementary architecture seamlessly integrates with SQL endpoints while preserving resource isolation. Improperly sized clusters frequently cause out-of-memory exceptions that crash long-running jobs and disrupt scheduled data refresh cycles across the platform. Here is a PySpark example for data transformation in Synapse using the read and filter methods on data frame objects. We read raw CSV data from AZ-305 Gen2, filter invalid transactions using column validation, and transform the date column with built-in parsing functions. Then we group by product ID to calculate aggregates before writing results back to optimized Parquet storage. This pattern demonstrates how Spark integrates seamlessly with the data lake for heavy ETL workloads while maintaining strict schema enforcement. The key takeaway is that Synapse Analytics unifies these engines into a single workspace, allowing you to choose the right tool for each part of your data pipeline while maintaining a consistent user experience and security model. You will enforce centralized governance through managed virtual networks and role-based access controls across all compute endpoints. This consolidation prevents siloed data architectures and ensures audit trails remain intact for regulatory compliance reviews during external vendor assessments. Let's check your understanding with a practical certification question. Which SQL pool type would you recommend for a data lake exploration scenario where query patterns are unpredictable and cost efficiency per scan is critical. You should select the serverless SQL pool option because it charges strictly by bytes scanned and automatically scales compute resources on demand. Choosing dedicated pools in this context wastes reserved capacity and inflates monthly operational expenses unnecessarily. To recap, we covered the Synapse Workspace as the central hub for managing all analytics resources within a single tenant. We compared dedicated and serverless SQL pools for different workloads, walked through CTIE's patterns for performance tuning, explored serverless querying with OpenROWSET, and examined Spark integration for big data processing. Mastering these components ensures your data platforms scale efficiently while maintaining strict security boundaries and predictable monthly compute costs across enterprise environments. For the AZ-305 exam, focus on distinguishing when to use dedicated versus serverless SQL pools based on workload predictability and budget constraints. Know the CTIE's pattern for performance tuning and understand how Spark integrates with the data, like using managed virtual networks. Remember that Synapse is a unified platform, so design questions often involve choosing the right component for a specific workload. Practicing these scenarios will help you avoid common pitfalls around compute scaling, limits, and misconfigured, or back permissions during certification assessments. Imagine a massive distribution center where goods arrive from countless suppliers, get sorted, packaged, and shipped to stores worldwide. Azure Databricks acts as that central hub for your data ecosystem, connecting diverse sources and syncs to deliver actionable insights. In this lesson, we will architect these integrations for scale. If you skip proper workspace isolation or misconfigure storage access policies, your pipeline will choke on latency or leak sensitive records directly into production systems. We will cover 4 critical areas for the AZ-305 exam. First, batch processing and ETL workflows using Azure Data Factory for historical data. Second, real-time streaming pipelines leveraging event hubs for continuous events. Third, enterprise data warehouse integration connecting to Synapse Analytics for reporting. Finally, machine learning orchestration patterns using workflow control nodes to automate your analytics lifecycle without manual intervention. Before diving into patterns, we must define Delta Lake precisely. It adds ACID transactions and schema enforcement directly to Azure Blob Storage or IDLS Generation 2. This architecture guarantees data consistency when multiple concurrent jobs update the same Parquet files. If you ignore schema evolution settings, your downstream reports will fail with type mismatch errors during peak ingestion windows. Let's look at batch ingestion using the Spark read CSV command. This script reads raw CSV files from IDLS Generation 2, applies a strict schema, and adds a processing timestamp column. We then write the curated data to a Delta Lake table using the overwrite mode. If you forget to enable time travel retention, you will lose audit trails when compliance auditors request historical snapshots. Databricks leverages the Spark engine to handle both batch and streaming workloads efficiently. While batch processing excels at moving terabytes of historical data through scheduled jobs, streaming provides fault-tolerant, exactly-once semantics for continuous data flows like IoT sensors or clickstreams. If you configure microbatch intervals too high, your dashboard will display stale metrics that mislead executive decision-makers. Here is a quick comparison of these architectural patterns. Batch handles large-scale ETL via data lake storage systems. Streaming powers real-time analytics directly through Event Hub's triggers. Warehouse integration connects Databricks to Synapse Analytics using federated queries for high-performance BI reporting. If you route heavy analytical scans through streaming endpoints, your cluster costs will spike unexpectedly and throttle live ingestion pipelines. Visualize the actual data flow across your architecture. Sources feed raw JSON or Parquet files into the Databricks Workspace Hub. The platform curates and transforms this information within Delta, like using optimized file sizing. Finally, refined datasets are served to downstream Power BI reports and Azure functions for automated decision-making. Misaligned partition columns will cause severe data skew during query execution. Now let's implement the unified workflow step by step. First, we ingest raw data from external sources into the lakehouse using system-assigned managed identities for secure access. We attach storage contributor roles directly to the Databricks workspace principal. If you hardcode connection strings in your notebook parameters, you will accidentally commit credentials to version control and trigger immediate security audits. This code demonstrates the ingestion step using the dbutils library. It configures secure access via managed identity, reads the CSV source from ID LS Generation2, transforms the data with a processing timestamp, and writes the result to the Delta zone. If you skip checkpoint directories for streaming sources, your job will duplicate records every time the cluster restarts unexpectedly. Next, we transform and stream the incoming data efficiently. We apply strict schema enforcement and process continuous events using structured streaming to maintain real-time insights. You must configure auto-merge rights for upsert operations on your target tables. If you ignore merge conditions, duplicate key conflicts will corrupt your dimensional models and break downstream reporting dashboards. This script connects to event hubs using Azure Service Bus credentials, deserializes JSON payloads, and streams the parsed data into a Delta Lake table with checkpointing for fault tolerance. We configure trigger timeouts to 300 seconds to prevent lag buildup. If you disable exactly once processing guarantees, your financial reconciliation reports will show phantom transactions during network blips. Finally, we serve and integrate the results securely across your organization. We expose curated tables via Databricks SQL endpoints for BI tools and register predictive models in MLflow for automated deployment. You must assign workspace reader permissions to specific service principals before exposing endpoints. If you leave default network access wide open, external scanners will probe your internal data structures. For the final step, use Databricks SQL endpoints to connect Power BI directly to Delta tables for fast reporting. Additionally, leverage MLflow to track experiments and deploy models as REST endpoints for automated scoring. If you skip model registry versioning, your production inference pipelines will pull outdated algorithms that generate inaccurate customer churn predictions during peak traffic hours. Remember this principle. Raw storage provides volume, but proper integration patterns deliver actionable insights. Mastering these architectural patterns ensures your architecture delivers measurable value efficiently. You must implement automated data quality checks using great expectations before publishing datasets. If you skip validation thresholds, corrupted records will propagate through every downstream report and trigger false compliance alerts. Check your understanding with a quick scenario. Which component provides optimized SQL endpoints for BI tools? The answer is Databricks SQL endpoints, designed specifically for high-performance queries. You must configure connection strings using private link service IDs to bypass public internet routing. If you expose endpoints over default networks, latency will spike and violate your enterprise security compliance requirements. We covered Delta Lake reliability, Spark batch and stream capabilities, SQL endpoints for BI, and MLflow for model management. These patterns form the core of Databricks integration architecture. You must document your workspace network topology and configure auto-termination timeouts to prevent idle cluster billing. If you neglect cost governance controls, your monthly Azure subscription will exceed allocated budgets unexpectedly. For the exam, focus on security patterns like managed identities and cost optimization strategies. You must know how Databricks integrates with Synapse, Event Hubs, and MLflow to design scalable solutions. Review the As Databricks Workspace Create CLI parameters thoroughly before testing. If you overlook network peering requirements, your lab scenarios will fail validation checks during the practical certification assessment. Imagine driving a car at night with no headlights or dashboard lights. You have no idea how fast you are going or when the engine is overheating until it fails completely. That is exactly what running production without telemetry feels like. Azure Stream Analytics acts as your real-time radar, processing millions of events per second across IoT Hub and Event Hubs. Without it, you risk missing critical anomalies in Power BI dashboards or failing to trigger automated remediation scripts before customers experience downtime. In this lesson, we will explore the core architecture of Azure Stream Analytics, walk through designing a job from IoT Hub inputs to SQL database outputs, and master windowing functions for temporal aggregation. You will practice writing queries that filter temperature spikes and join reference data tables directly in the portal. Mastering these patterns matters because exam scenarios frequently test your ability to configure low-latency pipelines that prevent cascading failures in distributed microservices architectures. Azure Stream Analytics is a fully managed cloud platform built specifically for processing continuous data streams with sub-second latency. You deploy jobs that consume millions of events per second from Event Hubs or IoT Hub without managing underlying virtual machines. This architecture matters because unmanaged compute bottlenecks cause massive backlogs during traffic spikes, while properly configured streaming units automatically scale to handle peak loads and keep your monitoring dashboards perfectly synchronized with live operations. At the core of every Stream Analytics deployment sits a single job containing 3 mandatory components that handle data flow sequentially. You must define inputs like IoT Hub or blob storage to ingest raw telemetry streams. Next, you write a SQL-like query that transforms and aggregates those streams using mathematical operations. Finally, you configure outputs such as Power BI or Azure functions to deliver actionable results. Misconfiguring any component breaks the entire pipeline and halts real-time reporting. Understanding the input and output ecosystem dictates how your pipeline routes data efficiently across different cloud services. You connect IoT Hub or Event Hubs to ingest high-throughput device telemetry, while blob storage handles historical batch imports for backfill operations. On the outbound side, you route aggregated results directly to Power BI dashboards, SQL database tables, Cosmos DB containers, or trigger Azure functions for custom alerting logic. Choosing mismatched services causes serialization errors and delays critical monitoring alerts. Let us examine the exact workflow for designing a production-ready Stream Analytics job from scratch. First, you register your IoT Hub or Event Hub's input and verify the JSON schema matches your expected payload structure. Next, you craft a SQL-like query that filters raw telemetry and applies mathematical aggregations across time boundaries. Finally, you attach output connectors to route processed records to downstream systems. Skipping schema validation causes runtime parsing failures that silently drop incoming events. Here is a representative JSON payload arriving from a smart thermostat directly into your ingestion endpoint. The structure contains a device-id string, a numeric temperature reading, and an event time timestamp marked in ISO format. That timestamp field proves essential because the engine uses it to order events chronologically rather than relying on arrival time. Relying on incorrect temporal fields causes window calculations to drift, which produces inaccurate averages and triggers false alarm notifications. Moving to the second phase, you concentrate entirely on crafting the query logic that drives your analytics pipeline. You validate input schemas as your foundation, then write a SQL-like statement that filters raw telemetry and applies mathematical aggregations across defined time boundaries. This stage requires precise windowing syntax to group events sequentially and calculate rolling metrics like moving averages or peak maximums. Incorrect window definitions cause duplicate calculations and overwhelm downstream storage endpoints. This SQL statement processes the incoming thermostat records by selecting the window end time and device identifier while calculating a 5-minute tumbling average. The timestamp BY clause explicitly references the event time column to guarantee chronological ordering before aggregation begins. A halving filter then restricts results to only emit rows where the computed average exceeds 25 degrees Celsius. Omitting the explicit timestamp reference causes out-of-order processing that corrupts historical metrics and generates misleading operational reports. Finally, you complete the architecture by configuring output connectors that deliver processed records to their designated destinations. You establish input schemas and validate query logic as prerequisites, then attach routing endpoints to forward aggregated results to Power BI workspaces or SQL database instances. This final configuration step ensures downstream systems receive clean, structured payloads ready for visualization or long-term archival. Skipping authentication setup causes connection timeouts that halt data delivery and leave monitoring dashboards completely empty. This configuration block defines a named output endpoint that routes processed records directly into a serverless function app. You specify the target name as Alert Processor and assign the type to Azure Function, which executes custom C# code upon receiving each payload. The Properties section includes the function app hostname and IPI key authentication parameters to secure the communication channel. Missing these credentials causes immediate rejection errors that prevent downstream automation from triggering critical maintenance workflows. Remember this fundamental principle. Streaming data holds equal operational value to archived records stored in permanent repositories. Capturing and analyzing events exactly when they occur enables automated remediation scripts to isolate anomalies before they cascade into widespread outages. You can deploy real-time filters that immediately route suspicious transactions to dedicated security queues while simultaneously populating executive dashboards with live performance metrics. Delaying analysis until batch processing completes guarantees missed response windows during critical incidents. Let us verify your comprehension with a practical scenario. You need to process events using fixed size, non-overlapping time intervals where each record belongs to exactly one partition. Consider calculating hourly revenue totals without any duplicate counting across adjacent periods. The correct approach requires a tumbling window configuration that enforces strict boundaries and prevents overlapping calculations. Choosing sliding windows instead produces double-counted metrics that inflate financial reports and trigger incorrect automated billing adjustments. To guarantee optimal pipeline performance, you must actively monitor streaming unit utilization and configure partitioning strategies correctly. SUs represent the underlying compute capacity allocated to your job, and exceeding 80% sustained usage triggers throttling that delays event processing by several minutes. Align your partition keys across all inputs and queries using explicit partition BY clauses to maximize parallel execution throughput. Neglecting this alignment causes single-thread bottlenecks that overwhelm storage endpoints during peak traffic periods. In this module, we examined the foundational architecture of Azure Stream Analytics and its mandatory job components. We constructed a complete pipeline by registering IoT Hub inputs, writing SQL-like queries with tumbling window aggregations, and attaching Power BI outputs. We also reviewed critical operational habits like monitoring streaming unit thresholds, applying timestamp BY for chronological accuracy, and joining small reference datasets directly within the query editor. Mastering these patterns ensures reliable real-time processing during certification assessments. For the certification assessment, prioritize mastering windowing distinctions and knowing exactly when to apply timestamp versus event enqueued UTC time. You must correctly match input services like event hubs with appropriate output destinations, such as SQL Database or Cosmos, DB based on throughput requirements. Additionally, recognize that reference data joins require small in-memory tables and always evaluate partition key alignment to prevent performance degradation during high-volume traffic scenarios tested throughout the evaluation. Imagine you are driving a car at night without headlights. That is exactly what running production without telemetry looks like. Azure Event Hubs acts as your high-performance gateway for ingesting massive event streams from IoT sensors and applications. It guarantees zero data loss during traffic spikes by buffering millions of records per second. Without this reliable ingestion layer, you will miss critical audit trails and trigger costly compliance failures in your architecture. In this lesson, we will explore the core concepts of event hubs, visualize how data flows through partitions and consumer groups, walk through implementing producers and consumers with code, and finish with key exam tips for the AZ-305 certification. You will learn to run as event hubs namespace create commands, set retention periods from 1 to 90 days, and avoid common misconfigurations that cause duplicate processing or dropped messages during scale events. Event Hubs is built for scale and durability. It can process millions of events per second, making it ideal for real-time analytics. Events are stored for a configurable retention period, allowing consumers to catch up even after outages. This decoupling lets producers and consumers evolve independently, while seamless integration with Azure services powers end-to-end pipelines. If you skip partition key configuration, you will lose event ordering and break downstream analytics queries that rely on sequential processing. Let's define a key term: consumer groups. A consumer group allows multiple applications to read the same event stream independently. Each group maintains its own offset, so one app can process data in real time while another archives it later, without interfering with each other's progress. You must assign unique names to each group and monitor checkpoint lag closely. Failing to do this will cause overlapping reads and duplicate billing charges across your Azure subscription. When designing your solution, choose the right tier. Standard tiers offer basic features and are cost-effective for moderate throughput. Premium tiers provide higher throughput units, dedicated resources, and support for larger consumer groups. For heavy IoT workloads or strict SLAs, premium is often the safer choice. Always calculate your required capacity in units before provisioning, because upgrading a namespace mid-project requires downtime and risks dropping active connections during the migration window. Here is how data flows through event hubs. Producers send events to the hub, where they are distributed across partitions based on a partition key or round robin. Events are stored in partitions for retention. Consumers then read from specific partitions within a consumer group and checkpoint their progress to track processed events. Misaligned partition keys will scatter related records across different nodes, causing severe latency spikes and breaking downstream stream processing workloads entirely. Now let's implement event hubs. We will follow 3 steps. First, create the producer client to send events. Second, process events with the consumer. And third, handle checkpoints and errors. Let's start by setting up the producer. You must configure your connection string securely using key vault references instead of hard-coding secrets. Skipping this step exposes your namespace credentials and allows unauthorized clients to flood your ingestion endpoint with malicious traffic. This code shows the producer implementation. We create an Event Hub producer client using the connection string and hub name. Then we create a batch to hold events efficiently. Inside the loop, we add data to the batch. If the batch is full, we send it and start a new one. Finally, we send any remaining events after the loop completes. Always set the maximum batch size to 2 megabytes to prevent memory pressure and avoid timeout exceptions during peak ingestion windows. Next, we implement the consumer. The event processor client manages partition ownership and load balancing automatically. You register handlers for processing events and errors. This client simplifies the complex task of consuming from multiple partitions in parallel. You must configure a lease container in Azure Blob Storage to track offsets reliably. Forgetting this setup will cause repeated rebalancing loops and duplicate event processing every time your application restarts unexpectedly. Here is the consumer code. We initialize an event processor client with the storage client for checkpoints and the consumer group name. We register handlers for processing events and handling errors, then start processing. The processor automatically manages partition ownership and calls our handler for each event. Always enable continuous checkpointing every 30 seconds to minimize data loss. Relying solely on end-of-stream checkpoints will cause massive replay delays after an unexpected service crash. Finally, we handle checkpoints and errors. Checkpointing marks the last processed event, allowing consumers to resume after failures. The event processor client updates checkpoints automatically when configured correctly. We also register an error handler to log issues and maintain system health. You must implement exponential backoff logic for transient network faults. Ignoring this pattern will trigger cascading retries that overwhelm your downstream databases and exhaust your allocated throughput units rapidly. This snippet shows checkpointing and error handling. In the event handler, we call update checkpoint async to mark the event as processed. This ensures that if the consumer restarts, it resumes from the correct offset. The error handler logs partition details and exceptions for debugging. Always capture partition context before updating checkpoints to prevent orphaned leases. Skipping this validation will cause duplicate processing across multiple worker instances during automatic failover scenarios. Remember this principle: decouple your systems to scale independently. Event Hubs allows producers and consumers to operate at their own pace, ensuring that spikes in data generation never overwhelm your processing capabilities. You must configure appropriate retention policies and monitor consumer lag metrics daily. Neglecting these operational checks will cause storage overflow alerts and force you to manually purge older events to maintain system stability. Quick check: what is the primary benefit of using multiple consumer groups in Event Hubs? A. Increased throughput for a single consumer. B. Independent offset tracking for different applications. C. Automatic partition rebalancing. Or D. Reduced storage costs. Think about it before we reveal the answer. Selecting option B ensures each application maintains its own read position without blocking others. Misunderstanding this concept will cause overlapping reads and corrupt your downstream data pipelines during certification scenarios. To recap, Event Hubs provides high-throughput ingestion with millions of events per second. Data flows through partitions and consumer groups, allowing independent processing. We implemented producers using batches and consumers with checkpointing via the event processor client. This architecture ensures durability and scalability for your data pipelines. Always validate your partition key strategy and configure capture rules to blob storage before deployment. Skipping these steps will result in untracked offsets and failed audit compliance during production rollouts. For the AZ-305 exam, focus on partition keys for ordering related events and consumer groups for independent processing. Know how to configure retention periods and use the capture feature for archiving to blob storage. Understand the difference between standard and premium tiers, and be ready to implement producers and consumers using the Azure SDK. Memorize the exact CLI command as EventHub's namespace, create, and always review throughput unit limits to avoid unexpected billing spikes during lab exercises. Imagine you're moving a massive library to a new building without an inventory list. You'll lose critical volumes and spend weeks searching for them. Data migration carries these exact stakes in Azure environments. Moving terabytes between Azure SQL Database and Cosmos DB requires precise planning to avoid corruption that halts operations. We will explore proven strategies like Big Bang and phased approaches using tools such as Azure Data Factory, ensuring your business data survives the transition intact and secure. We will compare Big Bang, phased, and parallel migration strategies, analyzing downtime risks for each. You will examine the ETL workflow powering migrations, reviewing Python scripts that transform schemas and validate checksums. We will configure Azure Data Factory pipelines with specific copy activities and monitor throughput metrics. Finally, we will cover security best practices like encryption at rest and exam-focused tips to help you design reliable data solutions that pass the AZ-305 certification requirements without causing service interruptions. Data migration is the end-to-end process of selecting, extracting, transforming, and loading data from legacy systems into target environments like Azure Blob Storage or SQL Managed Instance. This requires rigorous schema mapping and validation to prevent permanent loss. A failed migration can cause extended downtime exceeding 4 hours and significant business disruption. You must maintain integrity throughout transit by verifying record counts against source checksums. Otherwise, corrupted records will break downstream applications and trigger compliance audits. The migration lifecycle begins by assessing source data volume and defining the target architecture in Azure. You execute the migration phase where data flows through transformation pipelines using tools like DMS. Validation immediately follows, requiring you to verify integrity against checksums and exact record counts. Once validated, you decommission the legacy system. This loop ensures every byte is accounted for. Skipping validation risks silent data corruption that can invalidate financial reports or breach SLI thresholds before you notice the error. Big Bang migration moves all data in a single event, offering simplicity but risking hours of downtime that disrupt user access. Phased migration migrates modules incrementally, reducing risk while increasing architectural complexity and requiring careful state management. Parallel migration runs both systems simultaneously for validation, providing the safest path but doubling infrastructure costs across Azure regions. Select based on your tolerance. Choosing Big Bang for a critical ERP system could lead to unacceptable revenue loss during the cutover window. The ETL workflow implements most migrations by handling heavy lifting through extract, transform, and load stages. First, you must extract source data from the legacy system using connectors or IPIs. This step retrieves raw records while preserving metadata. If extraction fails to handle large datasets efficiently, you risk timeout errors and incomplete transfers. Always configure batch sizes appropriately. For example, setting a batch size of 10,000 rows balances memory usage against throughput when pulling data from a high-volume SQL Server instance. This Python script demonstrates extraction and transformation by reading a legacy CSV file row by row. It maps fields to the new schema, converts IDs to integers using int, and normalizes emails with regex patterns. The transformed objects are collected into a list and dumped as JSON. This code ensures data quality during the migration window. Failing to normalize strings can cause duplicate records or validation failures when inserting data into a target Azure SQL Database table. With extraction complete, the transformation phase cleanses, reformats, and maps data to the target schema. You handle type conversions, merge fields, and apply business rules like date formatting. This step addresses quality issues before data reaches the destination. Skipping validation here leads to garbage in, garbage out outcomes. For instance, passing a null value to a non-nullable column will trigger a constraint violation error during load, halting the pipeline and requiring manual intervention to fix corrupted records. You rely on specialized tools to automate migration steps. Azure Database Migration Service supports homogeneous and heterogeneous migrations with minimal downtime for SQL Server or Oracle targets. Azure Data Factory provides cloud-based orchestration for complex data movement across services. Apache NiFi excels at automating flows between disparate systems. For schema version control, Flyway manages database scripts. Using the wrong tool can result in unmanaged changes. Always verify compatibility matrices before deploying migration agents to production environments. You load transformed data into the target system by inserting records into the new database or storage account. Monitor throughput metrics and handle conflicts using upsert logic. Once loaded, run validation checks to ensure record counts and checksums match the source exactly. Ignoring conflict resolution risks duplicate entries that skew analytics. If checksums diverge, you must halt and investigate. A mismatch indicates data loss during transit, compromising audit trails and potentially violating regulatory compliance requirements for data accuracy. In Azure Data Factory, you define the load process using pipeline activities. This configuration specifies a source dataset and sink dataset for target storage. The copy behavior property controls streaming mode, while the timeout parameter prevents premature failures during large transfers. Setting a timeout of 3,600 seconds allows long-running loads to complete successfully. This declarative approach ensures reliable orchestration. Misconfiguring the sync connection string can cause immediate failures, blocking the migration and requiring pipeline restarts that consume additional compute resources. Never run a migration on production data without first performing a full-scale dry run in a staging environment that mirrors production complexity. This reveals hidden schema mismatches and performance bottlenecks before impacting real users. Test with realistic data volumes, such as 50 GB of transaction logs, to validate throughput limits. Skipping this step risks catastrophic failures. A dry run exposes timeout errors or resource constraints early, allowing you to adjust batch sizes and optimize queries before the critical cutover window opens. A company needs to migrate a mission-critical database with zero downtime tolerance and has the budget for duplicate infrastructure. Which strategy minimizes risk the most? Consider the trade-offs we discussed. Parallel migration runs both systems simultaneously, allowing validation without service interruption. Big Bang risks hours of downtime, while phased requires complex state synchronization. The correct answer is parallel migration, as it ensures safety through redundancy, though it doubles costs across Azure regions and requires careful load balancing configuration. Adopt these best practices to avoid pitfalls. Profile source data to understand volume and quality before moving anything. Implement automated testing with checksums to verify record counts. Maintain a rollback plan for every migration step using version-controlled scripts. Encrypt data both at rest and in transit using Azure Key Vault keys. Ignoring data quality leads to garbage in, garbage out outcomes. Unvalidated migrations can corrupt audit logs, trigger compliance violations, and force expensive rework that delays project delivery by weeks. Big Bang migration is fast but risky. Phased reduces risk incrementally. Parallel ensures safety at higher cost. The ETL workflow handles extraction, transformation, and loading across systems. Tools like Azure Data Factory and AWS DMS automate these processes efficiently. Always validate data integrity using checksums and encrypt the pipeline with TLS 1.2 to ensure success. Remember that skipping validation risks data loss, while proper encryption protects sensitive information during transit, meeting security standards required for certification exams. For the AZ-305 exam, focus on selecting the right strategy for given scenarios involving downtime constraints and risk levels. You will likely see questions about balancing Big Bang speed against phased complexity. Understand the role of ETL tools in orchestration and monitoring. Remember that validation and security are non-negotiable requirements. Expect questions on encryption standards and checksum verification to ensure you can design resilient data solutions that meet enterprise architecture criteria for cloud migration projects. Picture a massive library where every book is stacked randomly on the floor. You have thousands of volumes, but no index and no way to know which shelf holds history versus science fiction. This is exactly what happens when enterprise data grows without governance. Azure Purview solves this by acting as your unified index and map, helping you discover, classify, and trust your data across every cloud and on-premises source. Skipping this foundation will cause compliance audits to fail because regulators cannot trace sensitive customer records. In this lesson, we will cover the core pillars of Purview, walk through an automated discovery workflow with code examples, and explore best practices for implementation. You must configure scan rule sets for ID Lake Gen2 accounts and apply them to prevent unclassified sensitive columns from slipping into production reports. Understanding these components ensures you can confidently map metadata flows across hybrid environments without breaking existing security boundaries. Before diving into the tools, let's understand the landscape. Modern data estates are fragmented across SQL servers, data lakes, and SaaS applications. Purview provides a holistic map by ingesting metadata from connectors. It does not move your actual files, it only moves information about those files. This distinction is critical for certification exams. Purview governs metadata, not raw bytes. You will see exactly how the Azure SQL connector extracts table schemas without executing heavy queries against primary databases. Purview rests on three pillars. The data map is the backend engine that stores metadata and performs scans. It acts as the foundation. The data catalog is the user-facing portal where analysts search for assets using business terms. Finally, Data Estate Insights provides dashboards for executives to monitor governance health. Knowing which component serves which audience is a common exam theme. Remember that misassigning the data curator role to an executive will expose raw metadata tables instead of polished glossaries. Now let's look at the implementation workflow. We'll start by registering your data sources so Purview knows where to look. This initial registration step establishes secure connectivity using managed identities and virtual network endpoints. You must configure the exact storage account name and resource group ID to prevent authentication failures during automated scanning. Skipping this verification will cause scan jobs to fail silently. Here is how you register a scan for an ID Lake Gen2 account using the Azure CLI. The command specifies the collection and applies the system default rule set, which automatically detects PII like credit card numbers. You will execute as purview account scan, create with the exact resource ID, and apply the Microsoft classification rule set to catch unmasked social security numbers before they enter pipelines. Next, we configure the scan rules and classification logic. This is where Purview identifies sensitive data using built-in or custom rules. You must explicitly map these rules to specific container paths within your storage account to prevent false positives across unrelated datasets. Failing to scope the rule correctly will trigger unnecessary alerts on public marketing files, overwhelming teams with irrelevant notifications. This JSON snippet defines a custom classification rule for employee IDs. The regex pattern matches specific formats that system rules might miss. By adding this to your collection, Purview tags matching assets as sensitive. You will paste the exact regular expression string into the rule set configuration and target the H or container path to guarantee internal records are automatically flagged for encryption requirements. Finally, we establish data lineage. This connects Purview to tools like Data Factory to visualize the journey of your data from source to report. You must enable the Azure Data Factory integration within the Purview, account settings, and verify that pipeline run IDs are captured during execution. Neglecting this linkage will break the trust chain, leaving auditors unable to verify downstream reporting accuracy. Once scanned, you can query the metadata using KQL. This example searches for all assets tagged as PII within a specific collection. You will construct a custo query targeting the data assets table with a where clause filtering on the classification column to ensure audit teams can rapidly validate encryption status across your entire environment. A key principle for success is the glossary-first approach. Before scanning, define your business terms. If one department calls a customer a client and another calls them a subscriber, the glossary acts as the single source of truth. You must manually curate these terms in the Purview portal before running any scans, preventing orphaned metadata from cluttering your search results. Let's define the business glossary. This is a centralized repository of business terms that maps technical metadata to common language. On the exam, remember that glossaries are manually curated or imported, but they require active stewardship to remain accurate. You will assign specific data curator roles to domain experts who must approve every new term addition, preventing broken reporting pipelines. Here is how the data flows through Purview. Your source systems feed metadata into the scan engine via connectors. The engine classifies the data and stores it in the catalog. Consumers then search the catalog to find trusted assets. You must monitor connector health metrics daily to ensure that metadata ingestion does not stall, preventing stale tags from misleading decision-makers. Quick check. When should you use a custom classification rule versus relying on system rules? Custom rules allow you to define regex patterns for these unique identifiers, ensuring they are tagged correctly for compliance. You will apply this logic only when built-in classifiers fail to recognize internal code structures, preventing false negative classifications during external audits. We've covered the core pillars of Purview, from the data map to the catalog and insights. You learned how to implement automated discovery using CLI scans, custom classification rules, and KQL queries for lineage. You must validate every scan configuration against your organizational compliance framework before deploying to production, preventing misclassified assets from triggering regulatory penalties. For the exam, focus on the distinction between purview components and their audiences. Know when to use data curator versus data reader roles. Be prepared to identify integration points with Data Factory and Synapse for lineage. You will encounter scenario questions testing your ability to assign least privilege permissions correctly, ensuring junior analysts cannot modify critical classification rules. Imagine you are a master carpenter standing in front of a wall of tools. You have a hammer, a saw, a drill, and a chisel. If you try to drive a nail with the saw or cut wood with the hammer, the job will fail. In cloud architecture, we face the exact same challenge every day. We have Azure SQL Database, Cosmos DB, blob storage, and table storage. Picking the wrong engine leads to latency spikes over 200 milliseconds, massive technical debt, and bills that spiral past your budget caps. Today, we will build a systematic framework so you can confidently select the perfect data store for every exam scenario. Here is our plan for the next few minutes. We will start by breaking down the 4 key decision dimensions that dictate storage selection. Then we will look at the CAP theorem and how consistency trade-offs impact your design. Next, we will explore polyglot persistence and see code examples of decoupling your logic. Finally, we will cover best practices for managed services and exam tips to help you succeed on the AZ-305. Mapping requirements to Azure offerings prevents mismatches that cause costly refactoring later in your certification journey. Let's start designing the storage solution by analyzing the data structure. We need to determine if our data is structured, semi-structured, unstructured, or highly connected. This first step dictates the fundamental type of engine we must consider. If you misclassify hierarchical JSON as strictly relational, your queries will fail and latency will exceed acceptable thresholds. Verify schema flexibility before committing to a specific tier. To implement this analysis effectively, we use the repository pattern to decouple our business logic from the storage implementation. This code shows an abstract base class defining a contract for retrieving products. We then have specific implementations for MongoDB and Postgres. By coding against the interface, we can swap the underlying database without rewriting the application logic. Isolating interfaces prevents refactoring microservices during deployment. Next, we evaluate access patterns and consistency requirements. We must determine if the workload is read-heavy or write-heavy, and whether we need strong consistency or can accept eventual consistency. This step ensures the engine can handle the volume and latency constraints of your application. Misjudging write throughput will cause throttling errors when exceeding 50,000 request units per second. Align query patterns with target tiers early. Here is a configuration snippet for Azure Cosmos DB that demonstrates how we configure consistency levels. Run as Cosmos DB create to apply this JSON. We set the consistency level to session, which balances strong reads with good availability. We also define the MongoDB IPI and specify the location and failover priorities. This configuration ensures the database meets our specific latency and durability needs. Setting it to strong degrades global performance and increases monthly compute costs. Finally, we select the service and validate scalability. We must decide between vertical scaling for predictable workloads and horizontal scaling for massive growth. This final step ensures the chosen storage engine can grow with your user base without requiring a complete architectural overhaul. Relying solely on vertical scaling will hit hardware limits quickly and force expensive downtime windows during peak traffic periods. Design horizontal partition keys from day one. Let's compare the primary storage options side by side. SQL relational databases excel at structured data with complex joins and ACID compliance. NoSQL document stores handle semi-structured, hierarchical data well. Blob storage is ideal for unstructured files like images or logs. Graph databases are the best choice when relationships between data points are critical. This grid helps you quickly map requirements to the right engine. Wrong types cause performance degradation and increase infrastructure costs. Visualize how data flows through a polyglot architecture. A client request hits the API gateway, which routes to the appropriate service. The repository pattern acts as a router, directing the call to either a SQL database for orders or a NoSQL store for user profiles. This flow ensures that each piece of data is stored in the engine best suited for its access patterns. Misrouting causes latency spikes and violates service-level objectives during peak hours. A key term you must master is polyglot persistence. This approach involves using multiple types of data storage technologies to manage the different data needs of an application. Instead of forcing every piece of data into a single relational database, you use SQL for transactions, NoSQL for catalogs, and blob storage for media. This maximizes performance and cost efficiency across the entire system. Forcing entities into one engine creates unmanageable migrations and degrades response times. Now let's dive into the CAP theorem, which is essential for the exam. In a distributed system, you can only guarantee 2 out of 3 properties: consistency, availability, and partition tolerance. When a network partition occurs, you must choose between strong consistency or high availability. For example, banking systems prioritize consistency to prevent double spending, while social media feeds prioritize availability to keep the feed flowing. Wrong combinations cause data corruption during failovers or trigger unacceptable outages. Remember this pro tip for your design decisions. Unless you have a dedicated database reliability engineering team, prioritize managed services like Azure Cosmos DB or Azure SQL Database. The operational overhead of patching, backing up, and scaling self-hosted clusters usually outweighs the cost savings. Managed services let you focus on application logic rather than infrastructure maintenance. Neglecting this advice will consume hundreds of engineering hours on routine maintenance instead of delivering core business features. Let's test your understanding. You are designing a social media application that requires high-velocity writes and flexible schemas for diverse event types. The system must remain available even during traffic spikes. Which storage solution is the best fit? A. SQL database with red replicas, B. NoSQL document store, C. blob storage, or D. graph database? Think about the access patterns and consistency needs. Relational engines cause write bottlenecks and violate availability requirements during campaigns. Let's recap the key takeaways from this lesson. First, analyze your data structure and access patterns before selecting a technology. Second, use polyglot persistence to match the right tool to each data requirement. Third, understand CAP theorem trade-offs between consistency and availability. Finally, prioritize managed services to reduce operational burden and accelerate development. Ignoring these principles will result in rigid architectures that cannot scale horizontally and will fail certification scenario questions. Here are your exam tips for the AZ-305. Expect scenario-based questions that ask you to choose storage based on specific requirements like ACID compliance or latency. Focus on Azure services, Cosmos DB for multi-model NoSQL, SQL Database for relational workloads, and blob storage for unstructured data. Remember that managed services are often the correct answer when operational overhead is a concern. Skipping these areas leaves you guessing on architecture questions during assessments. Imagine you are running a massive library where every single book is stored on the top shelf. Retrieving a popular bestseller is fast, but finding a rare ledger from a century ago takes forever and costs a fortune in shelf space. That is exactly what happens when you try to use one storage technology for all your data. Today, we will fix that by designing a multi-tier architecture that balances performance with cost. Match Azure Blob tiers to access patterns, otherwise you waste budget or face latency spikes. Here is our roadmap for mastering this topic. We will start by defining the multi-tier strategy and why it matters for your architecture. Then we will break down the 3 specific tiers: hot, warm, and cold. After that, we will look at how to automate data movement using lifecycle policies. Finally, we will cover common pitfalls to avoid on the exam and in production, ensuring you configure Azure Storage correctly without triggering unexpected egress fees. Let's define our core term precisely. Multi-tier data architecture is a design approach where data is categorized based on its access frequency, criticality, and latency requirements. Each category is then placed in the storage medium best suited for that specific profile, ensuring you do not pay premium prices for storing rarely used data. Align Azure Blob Hot, Cool, and Archive tiers with actual workload demands to prevent unnecessary spending and meet strict compliance deadlines. Now let's look at the tiers themselves with concrete metrics. A typical architecture has 3 layers. The hot tier handles active reads and writes with high IOPS. The warm tier is for occasional access, like monthly reporting. The cold tier is for archival data that must be retained but is rarely touched. Studies show that over 90% of enterprise data is rarely accessed, making this tiering essential for controlling Azure storage costs. Let's compare these tiers side by side to see the trade-offs clearly. The hot tier offers the lowest latency but highest cost per gigabyte. The warm tier balances cost and performance for analytical workloads. The cold tier sacrifices speed entirely to minimize storage costs, often introducing retrieval delays of hours. Misjudging these trade-offs will cause application timeouts during peak reporting seasons or inflate your monthly cloud bill unexpectedly. Visualize how data flows through this system step by step. A user request hits the application layer first. The router checks the data age and access pattern. If it is hot, it goes to the cache or database. If it is cold, it routes directly to object storage. This decision point is where the architecture delivers value, preventing unnecessary IPI calls to expensive blob endpoints during routine operations. Now let's implement this strategy using practical commands. We will walk through the process step by step. First, we classify data based on access patterns to determine its tier. You must tag resources with metadata like tier equals archive and verify permissions before applying automated rules. Otherwise, you risk breaking dependent services or violating audit compliance requirements during routine maintenance windows. Here is how you classify data in practice using real metadata structures. This JSON metadata block shows the essential fields for tiering decisions. We track the creation timestamp and access count. The application uses these values to decide whether a record belongs in the hot tier or should be promoted to cold storage. Failing to update these tags will cause stale routing logic that wastes compute resources and delays critical audits. Next, we configure automated lifecycle rules to move data between tiers without manual intervention. This ensures data follows the classification logic consistently. Use the Azure CLI command as storage blob set tier or portal automation to enforce transitions, because manual moves will inevitably lag behind business growth and trigger unexpected egress charges during peak migration periods. This Terraform configuration defines the lifecycle rule for a storage container. It automatically transitions objects to cool storage after 90 days. It also sets an expiration rule to delete data after 1 year, keeping costs predictable and compliant. You must validate these policies with Azure Storage blob list before deployment. Otherwise, you might accidentally purge active logs or lock compliance archives prematurely. Finally, we monitor access patterns continuously to adjust our tiers effectively. Real-world usage often differs from initial assumptions, so you must validate your tiering strategy with observability tools. Track metrics using Azure Monitor and Log Analytics queries to catch anomalous read spikes early, because ignoring these signals will cause sudden budget overruns and degrade user experience during critical reporting cycles. This Python snippet shows application-level routing logic in action. The function checks the timestamp of a log entry using data time comparisons. If it is recent, it queries the high-performance database. Otherwise, it retrieves the object from Azure Blob Archive storage, ensuring the correct tier is used for every request. Misconfigured retries here will cause cascading timeouts and exhaust your compute quotas rapidly. Remember this principle as you design your solutions carefully. Tiering is about balance. You are constantly weighing performance requirements against storage costs. The goal is not to eliminate cost, but to optimize it for the value of the data. Align these choices with actual business SLAs, because over-provisioning hot storage will drain your monthly budget, while under-provisioning cold tiers will violate retention mandates. Let's check your understanding with a realistic scenario. You have a dataset of user logs that are accessed daily for the first month, rarely after that, and must be kept for 7 years for compliance. Which tiering strategy is most appropriate? You should select hot storage initially, transition to cool after 30 days, and archive permanently afterward to satisfy both latency needs and regulatory retention requirements. To recap, we covered the multi-tier strategy fundamentals thoroughly. We distinguished between hot, warm, and cold tiers based on access frequency. We implemented lifecycle automation to move data automatically using CLI commands, and we discussed monitoring patterns to ensure the architecture remains efficient over time. Master these concepts to pass the certification exam while preventing costly misconfigurations in production environments. For the AZ-305 exam, focus heavily on cost optimization and service selection. You will likely be asked to choose the right storage tier for a given scenario. Remember that cold storage often has retrieval delays, so ensure the business requirements can handle latency. Also, watch for questions about lifecycle rules and metadata tagging, because missing these details will cost you critical points on the performance-based assessment.